Hello, hello, hello. Immediately the stream layout broke. That's great. I love computers. How is everyone doing? I think there's barely anyone here, so let me quickly post on Fidi again. And yeah. We can wait for people to come in, hopefully. Okay. I hope the audio is working and that you can hear me just fine, including the background music. I think I tested it earlier, but I'm not sure if it's working right now. So yeah, let's see. I'm going to boost this on my socials again. And yeah, let's actually get rid of this. So stream delay is actually looking really really nicely. No music, you say? I mean, I'm pretty sure there should be music. It's probably very quiet. I did make it kind of quiet. I will make it slightly louder. That was just for the intro. We're going to hear the video itself much louder later on. Once there's actually a few more people here, I guess. I'll wait a bit. Excuse me. This is going up as a VOD anyways, so the plan was effectively to also have the VOD that I have the director's commentary for people. Thanks for people to refer back to later on, but I also wanted to do it as a live stream. Partially this also forced me to build a stream layout, which I do have now, and I'm pretty confident in the fact that it's working, mostly. Yeah, so let's see. I could stream via Owncast, but then nobody would stream the stream. I just got asked on Fidi. Yeah, so hey, there is a few more people now. Hello everyone. We're going to start the director's commentary in just a second. I am fully prepared. We have the video here. I am fairly certain that this is the longest video that I've ever made, or one of the longest ones that have at least this much effort put into it. I think the Pokemon Attack Mechanics video is also over half an hour long, but this one should be about the longest. So yeah, actually I think the story of how this came about. This is slightly interesting. Where the fuck do I have my notes? Here are my notes. Notes. I'm going to show you a little thing. Let's see if that loads over here. So The yes, I'm making a RISC-V instruction tier list. You have 2 attempts to guess 2 S-tier instructions. I just had the rough idea basically of making a tier list, and then like made this poll. And I'm not sure, but I think based on this poll, I was thinking maybe I should do it for like the entire instruction set. So yeah, this is also the poll results in case someone hasn't seen that yet. A lot of people voted for eCall and F-sign injection XOR, which I also have in my name now, which is probably the reason why people picked it. Also, a lot of people voted for LRSC, AOPC, mobile, high, signed, unsigned, and total store ordering fence. I'm pretty sure all the x86 people voted for the total store ordering fence. Okay, so like this was a pretty spontaneous thing, right? So 3 weeks ago, we're talking about does it say the time anyway? Yeah. So the 29th, the end of 29th of July. And basically I wrote the script on the 29th, the 30th, and the 31st, I believe. And I had an exam there as well, and then I was basically, okay, I have to get this video done now if I actually want to do it, otherwise I'm just gonna deal with it like all the other scripts that I have on the back burner right now, which is they're all getting put off and not entirely finished written. Like I have like 4 scripts or so 80% done. I have 1 video that is 1/4 edited, and none of these, like some of these have been laying around for actual years now. So I mean, there's also some scripts, I guess one of those at least, that I will never do. I just discarded the idea after writing most of it. But yeah, so basically I wanted to prevent myself from losing motivation on this project again, so I very quickly did all the stuff. Like I had Domi in a script review on Friday and Saturday, so on the 1st and the 2nd of August, and then I immediately started recording. I started recording on Saturday, and I did recording on Saturday, Sunday, and also Monday, because I had a bunch of fucked up footage. I can actually let's see if I can pull up the broken clip, like the past the last 20 minutes or so were all had to be done on a second battery because my first battery died. And at that point, my camera managed to reset its settings, and it went back to some blurry HD footage. Let's see if I can, for amusement purposes, show you the show you the fucky footage there. Maybe I've deleted all of it. Maybe it's in my trash bin. Let's see. Here we go. I think it might be one of those. And of course, VLC is still broken. Gonna have to open it in. Good thing that MPV works. Okay, music didn't break, no. Can't show you the video right now, I guess. I thought I had unfucked my my VLC, but quite obviously it isn't. Anyway, suffice it to say, there was some broken footage, and yeah, Just seeing now because I'm bad at reading chat and I don't properly have my chat open. I have my chat open on my other window. If someone were to make an x86 instruction tier list, it would be full of move, GF2PA, FFINEI, and VQB. Okay, I'm not gonna read all of them out. There is like a lot of crazy instructions in there. I guess GF2 is related to Galois field order 2, like GF2 Galois field operations, which those kinds of operations exist in RISC-V as well, just in the crypto extensions. So yeah, absolutely correct. So yeah, I guess that's my hint to kind of stop rambling. Though to finish the story, of course, to give you like an idea of the timeline, which was what I wanted to tell you about. Yeah, I finished recording on the 4th, and then basically edited 1.5 weeks straight, like usually about 8 hours a day, until and I had basically a hard deadline because last Friday, 1 week ago, 15th, was when I was going to visit my girlfriend, and PHMNP is for accelerating PHP. Okay. Yeah, so on the 15th I was going to leave for a short vacation, and that basically gave me the hard deadline, which was quite nice to work towards. And I had some mistakes that I could have gotten the video up on Monday, but I had some things that cost me a bunch of time, and I had to re-render the video a bunch of times. There has been like a lot of shit around there, and a lot of ProRes and DNX HQ intermediate renders and stuff. So yeah, a lot of stuff that got in my way, but I did finish it finally and uploaded it, and the analytics have been doing really nicely, which I've really liked. Let me actually see if I can show you the analytics real quick. I'll have to do some hackery here. I think I can switch. Yeah, and of course you're going to see the OBS now, but yeah, so there was this small spike. The algorithm liked the video at some point, which was really nice, and also people have been actually watching the whole thing, which even in the beginning was giving me quite a lot more views than usual for my videos, or quite a lot more watch time, which is very nice. Yeah, thanks Tim, by the way, for educating everyone about a really interesting x86 instructions. I appreciate it, and I think I really put in some effort to actually do some comparisons to other instruction sets, to like get in people that know other instruction sets but not RISC-V. Anyways, this is also it for analytics. Video has been doing nicely. It's slowing down a bit now, but I don't really care. Let's talk more about the actual... 1 second. Let's talk more about the video itself by actually getting into the video, and I'll talk about things as they come up. And yeah, so I think everyone is we have a cursed RISC-V extension now as well in the chat. Okay, nice stuff. Anyways, I'm gonna start playing, and of course, as you can see immediately here, there are only this intro was really the point here. Was really to show the equipment upgrade I guess I had. I mean, I'm still using the same camera. I'm using the teleprompter that I showed off on Fiddy at some point. Let me actually see if I can bring up that thing as well. But I got a bunch of very cheap green screen and softbox stuff. Like literally, I think half a month or so before I did this, so it was kind of also a perfect opportunity. And yeah. Let me see if I can. Where's my? Oh, here we go. Teleprompter shenanigans. I can possibly show you. Yeah. If you can see here, that's what the teleprompter looks like, the new one. I also have a better glass now, but yeah, that's also something I built. Actually, right, I built the teleprompter basically while writing the script and right before making the video. I think on the Saturday, so that was also like a really fun component in there. So yeah, and I just wanted to show off here, like doing kind of the fourth wall break here with the clap and introducing the background, like enabling the green screen. Really cool stuff. I guess I really like this intro. And by the way, yeah, the in case you're wondering, the music list, like I put a bunch of nice drum and bass into the video. The music list is in the top comment here, which, yeah, I didn't have space in the description in case you want to look at any of those songs. Most of them are on streaming services as well, so really nice stuff that I found there as well. So yeah, let's watch some video here. There are only a few things I really love in computer science, and apart from Rust, the first thing that comes to mind is RISC-V. I mean, I already did a whole talk on why RISC-V is. Yeah, I did this this talk, and by the way, this talk was also run through a RISC-V device, through the Vision 5.2 that Peter very kindly gifted me. I have gifted it further, but that was a nice thing. I mean, yeah, I'm just like, if you also combine Rust and RISC-V, that's also, I guess, the perfect thing for me. So awesome. I wrote 2/3 of the German Wikipedia article. Should have maybe labeled this bar chart, but yeah, this big blue part, of course, obviously is me. I mainly did like a whole architecture description, basically giving people a rough idea, putting a bunch of assembly code examples in there, updating a lot of the like commercial implementations that are available, uploading some images of microprocessors like ESP32s and stuff. Although like much of the like general structure already existed, I guess. Yeah. Some people gave me thanks for that edit. If you have no hobbies and you have too much knowledge about a niche topic, definitely go write about it on Wikipedia. It's always appreciated. On RISC-V, I own microcontrollers and a Framework 13 development mainboard for the sole reason of... Okay, here we go again. This is... yeah, I think it's called the Roma one. I just use this name because it's... because it's easier. I guess they have a longer name for it, the deep computing one. You can buy this in the Framework laptop shop, although I wouldn't recommend it because they're bringing out a second generation. This thing has a really shit graphics controller. It has some Imagination GPU, but it's basically the same SoC as the Vision 5.2. So if you want to get anything, please get the Vision 5.2 and not this piece of garbage. I mean, okay, it's somewhat garbage, but I will probably run it as a server in the future. But it is usable, and of course it works in the Framework case, so I guess that's nice. And the other thing here is, yeah, it's a CH32V203 on like a custom dev board that I made, which is, yeah, it's a tiny just a microcontroller, right? I could have might as well shown an ESP32 or something. I have a bunch of those as well, but that was the easiest one I could quickly grab. Don't think there's any in my room right now, or I mean, there is one in my room, but it's in operation. I can't just rip it out. An ESP32C3, which has a RISC-V core. So yeah, of them using RISC-V. A lot of people are focusing on either the microarchitecture optimizations or the firmware interfaces for RISC-V. Should clarify, like, I guess the microarchitecture stuff is like what I get into discussions with about people online, where I discuss, oh, wait, can you do macro fusion, which kind of design is nice for these kinds of hardware things, like is SVE, like is scalable vector stuff actually better for the hardware or not? Is it better for compilers or not? Whatever, like these kinds of discussions that we're having. But yeah, and like firmware interfaces, like that's what I noticed most, I guess, with Serenity and with Sönke, who I think is still in the chat. Is like there's you have to deal a lot more with just firmware stuff, with I guess like hardware registers or all the CSRs from the privileged ISA manual and that kind of stuff. And I had barely any idea before like we started porting Serenity of how that actually worked on RISC-V. I only knew about like the hardware, like the CSRs, but not really about OpenSPI and that kind of stuff. So, I mean, that's also, of course, what you have to focus on for firmware for operating system development. But on the other hand, I really like just the ISA itself, like the core part.
I, however, fell in love with the architecture because of the core that keeps it all together, the instruction set.
And I mean, the thing is, of course, the first thing I ever did with RISC-V is implementing the ISA, which means I am going to be biased. I'm going to like not I'm going to be biased. I'm going to be biased in the sense that I appreciate, yeah, the ISA is like the core, because that's the first thing like we read it in a uni course, and there are so few instructions. You can implement them relatively straightforward in like what did we do? Verilog, yeah, softcore FPGA stuff, and it's just gonna work. You can use a normal compiler and compile code for it, and that's kind of insane. And there's, I mean, you can do this somewhat with MIPS and some other like some other architectures, but it's these are all not modern and current, and there's not really any optimization effort in them. And yeah, this is just really nice that you have something modern that's actually being used in practice, but it's also incredibly good just for teaching and research, and you can write your own implementation very easily. You can write in like an interpreter, an emulator in software if you're not inclined to do FPGAs, whatever. That's also totally possible. I mean, I wrote the disassembler, and like most of the effort in the disassembler was implementing the compressed instruction set. So yeah. Anyways,
there are not a lot of RISC-V instructions.
Yeah, there are a lot of RISC-V instructions. That is a citation needed quote. Depends on what you look at. Obviously, we're going to see later on how that how that statement actually pans out.
But they're all so well engineered. But some of them are cooler than others. You've already read the title. Let's rank all of the RISC-V instructions from S tier to F tier. Anyone familiar with RISC-V will immediately notice.
And of course, the by the way, the footnotes are in. Where are the footnotes? Footnotes are in the description, and yeah, the important part really is that I did leave out a bunch of like variations of stuff, especially the floating point section. I left out like the single and double precision variants and all sorts of stuff, because it doesn't really matter, and it's the same thing. I don't really think in this case also single or double precision floating point is more or less important. I think it's like it depends on your use case. It depends on whether you 32-bit or 64-bit. Of course, if you're 64-bit, you might as well have double precision. If you're 32-bit, double precision is kind of overkill. So yeah, so that's also one of the main reasons why I didn't cover a bunch of variations and didn't talk about like all specific things and parameters you can pass to every single instruction. And like this is also the big debate: how many instructions are there, depending on how you count it. This goes for other ISAs, by the way, as well. For x86, I think it's like really complicated to count. I saw like some counts that vary by a factor of 10 or whatever, depending on how you count x86 instructions. Yeah.
that this video is way too short to fit literally every single standard instruction. Yes, just now I said there are not a lot of RISC-V instructions, but once you get into stuff like the cryptography and vector extensions.
This is, by the way, like an unshortened list. I thought the list was going to be shorter, but it actually ended up being that long. And it's like stitched together a bunch of stuff that I stitched together in an image editor. So this is multiple pages of just listing out the encoding for certain vector instructions. And I think this is not even, oh no, actually, sorry. You can see up here like AES and SHA-2 or whatever. So this is actually including the vector extensions, but a lot of these are like normal floating point stuff.
That's not really.
And like, I mean, there's just so many things you can do with vectors. It's really understandable. The vector instruction set should have been designed differently. Like they should have just gone to 64-bit instructions and then had a proper like third or fourth register, a register operand for specifying a mask register, and then having proper mask registers, right? And that would have probably released a lot of the pain of the current vector extensions, which all have like hard-coded vector mask register at V0, which is probably the shittiest design decision in RISC-V. Like overall, I would give V a pretty low tier because of that. But luckily, I kind of ran out of steam before I got to V, or said I'm not going to handle that many instructions. Same with B, by the way. I didn't want to like learn all of that, and there's also a lot of instructions. Video would have been like twice the length, so I kind of just didn't deal with it. Limited myself to G and the other stuff that I did.
There are a lot of vector instructions. The specification in the 2024 edition has grown to over 600 pages.
What's funny is that when I started writing, or when I wrote at least this part of the script, I didn't even know that there was a 2025 edition of the spec yet. And then I panically, while editing, I found out, and I panicked and like looked at the 2025 spec. Luckily, there's basically no changes. There's a bunch of extra extensions in there. It's slightly longer still, but not much actually. Like the difference between the 2019 and 2024, between like 200 and something pages to 600 and something pages, that is quite extreme, and that is probably the most extreme it's gonna stay for a while. So yeah, the point still stands.
That's about 3 times as large as the previous one. So what I've done is limited myself to the base architecture as well as the most commonly used extensions. This is the G extension group, as well as.
By the way, this is a good point in time to talk about the font. The font is M+1MN, and it's used it used to be used in the manual as like a fallback font, but then it ended up being used as like all of the code fonts, basically all of the code snippets and like monospace stuff in the spec is in this font, or used to be in this font in like the 2024 edition. And in the 2025 edition, I think they quote unquote fixed it and are now using JetBrains Mono. So the font that you will use, it's from Sea Lion or whatever. I'm not sure why they did it. I really like 1+1MN, and that's also why I used it for the video. But it was like kind of an intermediate thing, because the 2019 edition is basically LaTeX default style, so it uses Computer Modern and the default monospace font from LaTeX. Just interesting. Yeah, anyways.
Some subjective choices I made. I mostly...
Yeah, I included the hint pause because I think most things that have G also included, and I included the cont because I really liked it. Like I looked at it briefly and I was like, oh, that's really nice. It's also just basically 1 or 2 instructions, so I can easily include it. And I think it might even be mandatory in RV 24A. SPHolz might know. Yeah, GC of course is also very common. Yeah, that's like the big thing that I forgot to forgot to address. I'm going to have to look out for my notes here. Yeah, compressed instructions is something that I basically entirely missed. Handy at Jorn pointed it out to me before the stream. I have a comment about it on the video that asked it in which tier does compressed instructions believe. Okay, and I also just got the confirmation from Esperholz that ZICont is required in RVA 23, so it is required in, like, at least in the future, if you're going to get desktop and server systems RISC-V, you're going to have ZICont anyways. And yeah, as I say in the video, we'll get to that towards the end. I actually really like this extension. Anyways, briefly, yeah, while we're like have the list of the the extensions that I'm going to look at, I didn't look at compressed instructions because the C extension itself, which is GC, which is very common, and also most microcontrollers have compressed instructions, they are just a different encoding for the same instructions. Like, all of them map one-to-one to existing instructions from the G extension set. A large part of them map to like the base ISA, and a few map to the floating point extensions. And there are some further like extensions in like the ZC, so, or ZC groupings. There's like a bunch of extra compressed instructions that do things that are more complicated, but those are also partially incompatible with G. Like, there is one for pushing and popping multiple registers, and they're really intended for like embedded systems or like microcontrollers where you really need strong compression, very small code size. And I think that one is actually incompatible with G, or at least with some like very common extensions, so it's never going to show up in desktop systems. So if we're talking about just base C, it is literally the exact same instructions. My general opinion on it, I can still give, of course. I hated C. I think it's terrible. Or like, I think it's terrible in the sense that I don't think it's necessary, and I think this in a scientific way. My scientific academic opinion is that C is unnecessary for desktops because, oh yeah, it's incompatible with the standard ABI, the extra extensions, I was informed. So yeah, okay. So yeah, as I was saying, I think for desktops, C doesn't matter. There have been analysis on this. The instruction, the size, the code size from RISC-V without C compared to like x86 and ARM without thumb is slightly higher, but not significant. It is not significant in the sense that instruction access patterns are actually really predictable, and like instruction streams can make really effective use of caches and high memory bandwidth that we have in desktop systems anyways. So C is fundamentally something for microcontrollers. It is intended really for places where you need 20 to 30% code size reductions, which is what C roughly gives you. Which I think, yeah, it's fine for microcontrollers, but my opinion is that it should have not made it into the desktop standards, basically. I think the desktop standards would have been better off without it. Would have like reduced like a lot of alignment issues. Like, if you think about it, like a lot of the even the really complex desktop stuff is all 32-bit instructions. Like, the front ends would have had a lot less work if they just had 32-bit instructions. That's my personal opinion. I've seen some of the implementation details, for example, in the CVA6 processor, which is an open source like 6 or 8 stage in order, slightly superscalar implementation, which I think implements GC as well, and they have some realigning stuff in the front end. It's like somewhat cursed. It's yeah, basically, I don't think it's worth it. Like, I think it's worth it for microcontrollers, sure, same way that thumb code is, but like, that's also the reason why I don't think thumb is used on ARM desktop I think it's even mostly not implemented on ARM desktop, but people might correct me that know more about ARM. But this is like the same, basically, yeah, the C extension occupies the same niche as Thumb, right? It's intended for like strongly memory constrained embedded systems. Yeah, AH64 doesn't support Thumb. So here's my point, right? 64-bit ARM doesn't have quote unquote compressed instructions, doesn't have Thumb. Even though Thumb and C are not exactly equivalent, they work slightly differently. Also, the way you invoke them. And Thumb is slightly more cursed than C. Like C is generally not super cursed. Just the encoding of C is also extremely cursed, and I hate it. And yeah, I know. Like, I'm not saying the Thumb wasn't used. I'm saying that and I'm also not really talking about phones. Like, I'm not talking about mobile non-embedded. I would call phones not really embedded systems, in the sense of like microcontrollers and fixed function stuff. But yeah, so like I think for phones it might, yeah, or at least it used to be worth it, right? I don't think it's worth it anymore, or it might not be worth it anymore. Don't really have a strong opinion on that. I just think if we're talking about, yeah, desktop systems, just throw it out, right? It's I don't like C. I'm not sure what the profile, like the RISC-V profiles, say about this. Like, I'm talking about the profiles a lot. I maybe should have explained that. Basically, profiles are a more proper and more updatable something Giselle. The profiles are a more general grouping of certain extensions that are, some of them are also optional and also include like privileged stuff. So for example, virtual memory requirements. They are basically intended, yeah, for server and what is it called? Server and desktop stuff. And they're, yeah, supposed to be like a baseline for both hardware and software to converge towards, if you're talking about the higher performance end of RISC-V. Because microcontrollers embedded will always have like very different requirements depending on the exact system size. Things have to be flexible there, which is also the main advantage of RISC-V, right? But on the server and desktop end, you need to converge and standardize, and that's what the profiles are for. So if you're looking towards what your average Linux system, what your average laptop will do in, let's hope, a few years, you should look at the profiles, which is what hardware vendors will look towards, and which is what our Linux and other operating systems will look towards. And also, if you're like, yeah, if you're getting pre-built binaries, the binary might be aligned to like run on systems with that profile. So a lot of things will converge around that, I hope. And like G in general is it's a fairly outdated thing now. It's not really like you're going to target specifically G. It's going to be the baseline still, but it's going to include a lot of extra stuff that you might want. It's not going to include a lot of extra stuff that you might want. So that's why G is not really generally useful. That's also why I don't really like referring to G. It's just, it's this like rough early days grouping when the RISC-V people didn't really know what they were doing, in that sense. And like the profiles is the main thing that we wanna look at. Anyways, I've talked for quite a while, so let's watch some more.
Using the order from the specifications instruction listing, so there should be no dramatic bias. Let's go.
Of course, actually, I forgot to talk about this earlier. I forgot where did I have the tier list? Here I had the tier list. So let me quickly go back to the tier list. People complained that the tier list was like these abstract numbers, S, A, B, C, D, F. I agree. I could have given them better names. I just, I guess I really liked like the traditional format here that is recognizable, and that's also great to put in the thumbnail, I guess. And yeah, Does RISC-V enable us to build Rick's portal gun? I don't think so. I don't know what Rick's portal gun is, pro proxy. You might have to re-ask me that question in person once we see each other again. Anyways, so yeah, I could have gone with a different format with like calling the tiers, for example, and that's what they roughly are, right? So S tier is roughly absolutely brilliant design. A tier is great above average design. B is average design for a RISC instruction set, and necessary and boring stuff. C tier is like kind of a little bit slightly slightly worse than average, I guess, or like slightly unclear what it's for, or slightly weird why it exists and why it doesn't exist in another form, for example. D tier is yeah, I really don't understand why it is here. What the fuck is it doing here? Can we just get rid of it or change it completely, and so on. No, I didn't watch Rick and Morty. All the S mode instructions, of course, go in S tier. Yes, SRET, of course, needs to go in S tier. SRET would honestly be something that goes in B tier, including MRET. I don't think those are particularly genius. Just like boring necessary stuff, right? And also like F tier would have been stuff that's CISC, I would say. And like some of there are some instructions in RISC-V that would go into F tier, definitely, in some of the weird extensions. But in the core, and then also a lot of I guess, or at least some vector instructions would go in there. But also there are some vector instructions in S tier, like vset VLI is in S tier, for example. Anyways, no, like I didn't put anything in F tier to make a point, right? The point was that I think I say this at the end of the video as well, but like the point was nothing really is terrible here. This is an extremely well-designed instruction set considering everything else that we have. And that is one of the main points I guess you should take away from here. Anyways, let's start with the
Let's go.
This. Also, here's the first and major mistake. There should be an I here. This is RV32I, which is the base integer instruction set for 32-bit. So RISC-V 32I. And this is catastrophic because like I don't know how I could have missed it, and SP Holz immediately noticed that I made this mistake. So fucked. Anyways.
Ah yes, the base instruction set. This is the one I mean when I say RISC-V has very few instructions, because there are only 40 instructions here.
Yeah, as I say in the footnote, I think I count 42. 40 is what the spec itself says. I really just went with a spec number there to not have any people actually me about this. Which I can always say, oh, the spec says so. Please complain to RISC-V International. Also, this background is really cool. This is like doing optical flow, and like it's recolored. Also, yeah, that actually. Let me jump back over here to this background here, because that is actually the. Like this background with like the floating stars and shit, that's actually made by me and Anna over when Anna was over. Like we spent a few nights building this thing in Blender. It's like the first time I've ever touched Blender, and I made some slightly cool stuff with Blender and in shader nodes and shit. It's really nice. Anna should upload it to its website at some point, or at least I told it to do it. But yeah, anyways, I made this background specifically for the video. I might also release it at some point under Creative Commons somewhere, but I haven't really gotten to that yet. So yeah, let's jump ahead to Louis again.
Here. what better place to start than the very first instruction from the 32-bit base instruction set?
I mean, of course, first in terms of the order that is in the instruction listing, which I don't know why Louis is first, but it might be like just numerically speaking in terms of the bits, I think.
Load upper immediate is rather self-explanatory. It loads a 20-bit immediate into the upper bits of the 32-bit target register. The interesting...
Yeah, it also clears the lower 12 bits in the subtitles here as well. Subtitles are not auto-generated, by the way. I never auto-generate my subtitles. And it's also sign extended. I used to think that the U stands for unsigned, but I was always just stupid. It's load upper immediate, not load unsigned immediate. So that's like a funny oopsie that I had in the past, I guess. Yeah. So yeah, and it says here on 64-bit, it sign extends the upper bit. But like for this part also, we're going to kind of focus on the 32-bit instruction set, although like most of these instructions, the extension to 64-bit is quite trivial, and the default case for RISC-V is generally sign extension with very few exceptions. So that's something you can keep in mind here.
Part is how RISC-V encodes this and other instructions. All instructions are 32 bits, and the encoding includes operands in those 32 bits. Therefore, we can't really have an instruction for a 32-bit immediate load. Obviously, there's not enough space for a 32-bit immediate in a 32-bit instruction. The solution to this problem is very clever. Instead of loading the full 32-bit value in one go, what if we instead loaded the upper part of it with this Louis instruction? The encoding reserves 20 bits of space for an immediate.
Yeah, this might just be the first one, I guess, with like 0, what is it? Yeah, 10110. I don't quite know. So I'm missing the columns here, of course, but this is the major opcode column. First 7 bits, then you have 5 bits register, and then the immediate, which also it's like, yeah, this is super trivial. You can just leave out these parts and just pass these bits through. It's just so cool how RISC-V manages to make the immediate generation in hardware extremely cheap. But this is not something I really talked about here, but this is like one of the major things. Like all of the immediate bits are usually scrambled, so to speak. Like they are scrambled, but in a way where they line up as much as possible between vastly different encodings, so that you can keep the base the same immediate generation like logic. Like your combinatorial logic for generating immediates in hardware can be a lot simpler. The J-type immediate is my favorite. Oh, we're going to see the J-type immediate in just a second. Actually, while we're at this, I might as well also pull out the spec so I can actually show you the priv. No, not priv ISA ASCII doc. The unpriv ISA ASCII doc from 2024. Where do we have the instruction listing? Here we go. Then I can like do this thing and quickly hide my OBS. Yep. So yeah, I mean, this is also what I talked about. I think I talked about this later, where like, yeah, the J-type immediate just gets fucky over here. So yeah, you can see here, like, I didn't talk about this either, but the instruction encodings follow some pattern. There are some general schemes here. There is like R-type, which has 2 registers, I-type, which has a larger immediate, S-type, which is for a store, which doesn't have a destination, B-type, which is a branch, which is like an S-type, but it's missing the lowest bit because you only can have to 16-bit alignment branch, so you can like put in an extra 11th bit in here. If you like see, always the top 31st bit is always the sign, so you can always sign extend that. That's one of the ways that this makes hardware fast. And yeah, the U-type and J-type you can see here are almost the same, but not quite. And like the point is that J-type lines up with B-type and U-type doesn't line up with anything. I still think that's silly. I still think they should have shuffled it a bit around to make U-type and J-type line up at least almost. I'm saying that from someone who had to implement this in hardware, right? I've implemented an immediate generator. I've seen what the RTL logic that drops out of this looks like. I don't like this one, but yeah, this is really funny. Also, if you don't know about the syntax, I think I never explained this. This means like, yeah, from bit 12 on the left up to bit 19, from bit 12 on the right up to bit 19 on the left, inclusive on both ranges. This is like very normal syntax for hardware description languages. It's quite weird if you just know about software stuff, right? But I guess I just drop this on you in somewhere in the middle of the video. Let's continue watching. Yeah.
Then we add the remaining lower 12 bits on.
Ah, yeah, here we go. Here you can see the syntax as well. So we have inclusive bit 0 and conclusive bit 11, and so on and so forth.
To this value by means of an add immediate.
And yeah, I think it's quite obvious that this is supposed to be an add immediate into destination registry, because the syntax, but that's probably only uncommon if you don't know assembly. Syntax is always destination, comma, source.
Immediate instruction. Every 32-bit immediate load.
Yes, I am cute fitty person. Hi, Leah.
Becomes 2 instructions, but more instructions does not automatically mean more bad in RISC land. In fact, it almost never means more bad.
Yeah, this is something I've talked about earlier, right? All of this stuff, and of course in like the macro op fusion in superscalar processors, there's like a lot of kind of complicated macro op fusion that people have come up with for RISC-V, which is at least was documented on some wiki somewhere. Like there's some really cool stuff you can do, which is like basically automatically aligned with the stuff that compilers generate, because it's just the natural way to generate code. It would be nice if we had a better spec for this, I guess, but it's also fine. Like you will also always figure out more and more optimizations in hardware that as time goes on based on existing code, and I think that's totally cool. And that's also the thing with RISC, right? You don't have to hard code the optimizations that are relevant right now into the instruction set. You can only hard code, quote unquote, hard code the what is it called? The optimizations that you that you really actually think you'll need forever, basically, and leave everything up to the vendors to do. And hopefully if vendors compete not on ISA but on the actual implementation, which is the point of RISC-V, then you'll get faster hardware. That's at least the goal. Let's see how this pans out.
So Louis is there to perform the first part of the load. It's one of 3 instructions that reserve an absolutely massive part of the encoding space for 20-bit immediates.
Yeah, if we go back to the to this thing, then you can see this is the base opcode map, and like Louis has one separate space here. Well, I showed this later on with the fused multiply add, which has this space, which is even more, but you have Louis here, and you have JAL here, and you have RISC-V here. So these 3 with like the J-type immediate, U-type immediate, U-type immediate, and then the fused multiply adds as well. They take up quite a lot of space. I've actually since, by the way, figured out that ARM is very similar. ARM has the same thing, basically equivalent to an RISC-V instruction. ARM also has the fused multiply add instructions. So like a lot of similar choices were made there. I guess it all makes sense. Yeah.
And for a very good reason, of course. While 12-bit immediates are enough for some purposes, 32-bit immediates are enough for basically anything, including on 64-bit systems. A tier for Louis. If you thought...
Yeah, definitely best named instruction, RISC-V, definitely.
Louis had a funny name. You clearly haven't met RISC-V yet. Add upper immediate to program counter. Once again, once we actually know what the acronym means, it's easy to figure out what it does. We take the same 20-bit upper immediate as in Louis, but instead of loading it directly into the register, we add it to the value of the program counter, i.e. the address of the RISC-V instruction itself. Now the obvious question is, what the fuck? Who needs that? Why do I care about the program counter if I'm not doing a jump? I can't even write to the program counter with this. Well,
that's of course the excellent setup for, well, you do actually care about the program counter, but in a very roundabout way, which I think is like the coolest part about RISC-V. Because when you see this for the first time, like literally when we implemented this in our course, I was like, the fuck? Like this was my exact reaction. Like, what the fuck is up here? Why the fuck? And then I noticed, oh wait, yeah, like code relative, like oh my god, that, yeah, like you get position independent code for free. Holy shit, this is the best thing in the world. Anyways, this is like old knowledge, by the way. This is like stuff that ARM also has. So it's not like it's new, but it's super cool to discover. And also nobody told us in the course that I took. Nobody told us why RISC-V is useful. I guess they could have told us, because also it's in MIPS, and they, like all the people that did the course, are very familiar with MIPS, obviously. And they had only been doing RISC-V for a few years at that point. But yeah, MIPS and RISC-V are of course very close as well. So yeah. Anyways,
there is one obvious thing we can do with this instruction, which is simply reading the current program counter. Sometimes I guess that's useful, but in theory this is also possible by doing a jump. But that's not really the point of RISC-V. The point is really to load code offset addresses.
Wait, I'm gonna jump back.
In theory, this is also possible by doing a
yeah. So of course I'm just like dropping this code in here without any proper explanation. If you've seen the video already, I guess you know what jump and link does. Jump and link writes the next address to the destination register, which here is T0, just a temporary register. And 4, of course, is relative to this instruction. If we assume, and we can force it, if we assume this instruction is 4 byte long, then this just jumps to the next instruction, which has the effect of basically not doing a jump at all. Yeah, so this stores, and of course the program counter address that is stored is the one from the next instruction that would be below here. Which, yeah, that would be possible. You could like remove RISC-V in that sense. You couldn't do the add, but you could remove it in that sense. But of course, this will put pressure on like all of the branching stuff, because this is technically a branch. And if your microarchitecture is not super smart about eliminating these kinds of branches, this will still fuck up your performance and your pipelining capabilities. And that's generally why we want to have at least as few branches as possible. Obviously, that's like basic optimization thing. This is true on all architectures.
Jump, but that's not really the point of RISC-V. The point is really to load code offset addresses. What I mean is that a lot of program data, be it the global offset table of function pointers, function's address we want to call, some static variable, and many more, they all have a fixed position, at least relative to the code that we're currently executing. Obviously.
Yeah, I mean, this is this really depends. I'm not even sure. I'm pretty sure this is true for like normal PIC elves, like position independent elves on Linux. I haven't actually checked, but I think they all just have their address, and then yeah, they are ASLR marked, and the kernel just relocates them on startup. I'm pretty sure this is the correct thing. And like, yeah, the global offset table from libc, of course, will I think actually I don't know, but I'm pretty sure, like, yeah, I mean the global offset table is a table that points to functions in libc, as far as I know. I'm not super familiar with all of the details here, but yeah, so it is like the GOT is per shared object, per executable or library, whatever, and it gets filled in on load once we know where libc actually is. So you can have pointers there to libc, or you can have more complicated stuff where like you can have things where you jump into the GOT, or the GOT points to some fix-up code. So the first time you jump there, the fix-up code runs, which then determines the address and then writes it to the jump table. And then the next time you jump, you don't go through the fix-up code. So you have like a slight penalty, but you have a faster startup time because you don't have to like fill in all of the addresses of like the many thousand libc or other functions from other libraries. Like there's various ways of doing this, but this is really outside of the scope of like RISC-V architecture stuff, right? It's kind of extra things that are also valid for other architectures. Yeah, but static data at least should be static, should be positioned statically in relation to code, and function addresses as well.
All
them
code
definitely,
is fixed
yeah.
relative to all other code. Otherwise, it would be pretty damn hard to run it. But even static data segments like .data and .bss usually have fixed positions somewhat close to the code. What RISC-V allows us to do is load a constant address like that by loading its fairly small offset from the current instruction address. What I actually find kind of unintuitive, and what some very primitive assemblers do differently, is that with RISC-V and in assembly, you don't specify the lower 3 bits. You just, in this case, 44. And then you have implicitly the 3 zeros there. So I think, yeah, when we did our development of our softcore, we had an assembler that didn't actually handle this properly. Like you had, in this case, you would have to write 0x44000, so specifying the extra 12 bits, which is super silly. But for GCC and LLVM, this is definitely true. So the syntax, I could clarify this up specifically. Like the syntax that I'm using is a syntax that the manual recommends. There is no full assembly manual yet. It's kind of shit that this doesn't exist, or it's like totally incomplete. But like this syntax is followed by both the GNU assembler as well as LLVM. So if you're using any reasonable toolchain, if you're writing C and C++ and Rust code and so on and so forth, you're going to be using this syntax. And yeah, I've seen some, like a few days ago, I saw some really weird syntax that maybe, or at least Microsoft's compiler used to use, but it also looked ancient, and I'm not sure if it's actually x86 code in disguise. So let's not talk about that. Anyways, this is like standard syntax, right? So, and this is this kind of sequence with RISC, register, upper thing, ADDI, and I guess you can like remove the second one or same register twice, and like lower 12 bits. This kind of sequence, I feel like, is every third instruction in RISC-V sometimes. I mean, there's some sections in code where you can really see this kind of sequence a lot. It's something to really look out for. And of course, adding another 12-bit offset with a secondary instruction if necessary. As we'll see later, adding this offset is also possible with a load or store directory. Yeah, so this is the first bit, I think, of real code. All of the code is from a very, very old compilation of Serenity OS. There's a lot of Serenity people in the chat. Hi, everyone. I mean, I did post this on the Serenity Discord, so I'm not surprised. But yeah, this is like ancient Serenity compile that I just had laying around and disassembled a bit and looked around for good examples. Yeah, so this, for example, is a stack check guard, which is like one of the protections against stack smashing. This is like part of the standard code sequence, but in this case, yeah, we have to read the stack check guard, so we have to do a load here, and because the load can also specify 12-bit immediate, as we'll see later, like loads don't add another instruction, so you don't have to do RISC, ADDI, and then load. You just have to do RISC and then load, and that's also great. And that's, yeah, I think there's you can tell that all of these instructions were designed in one go, with like very specifically making these kinds of sequences really nice.
And that's like one of the great things where you basically get these aha moments where you realize, I know what the designers were intending here. Like you can really see the design intent here. Meanwhile, when you read x86 code, you're like, okay, I guess some random Intel engineer thought this function, this instruction might be useful for someone somewhere, so he just put it in, and it didn't get removed from the HDL before they shipped the processor or something. That's sometimes what x86 feels like to me. Not to shit on x86, but it is morally correct to shit on x86. The only instruction set you're allowed to shit on more than x86 is S390X, because S390X is objectively the worst instruction set. Let's not get into that.
So if we're performing a memory access, we also only need 2 instructions. So RISC-V is super useful, as you can tell. In fact, you'll see any RISC-V disassembly littered with RISC-V instructions. But it's not just useful, no, this is where RISC-V earns its S tier. It makes position-independent code trivial. Let's learn about something fun called address space layout randomization.
Ooh, ASLR. Yeah, I did sneak in some more general stuff, I guess, here. And this is like, this section is specifically one of the very general ones that are applicable to all architectures, almost all operating systems. I don't know if it's applicable to Windows, but it's definitely applicable to all Linuxes and all Unixes, all modern Unixes. So, yeah.
For security reasons, we really want our programs to never be located at the same place in memory twice. We want the address to be random each time the program runs. This,
I guess I could give some more context. I mean, you can also look this up. This is one of the basic things you learn about binary exploitation very early on. The thing is, it's somewhat easy, or at least sometimes it's relatively easy to leak a pointer from a program, and then you know where stuff is located, or when you know what the pointer is pointing to and where things are in relation to that, or at least you can figure out things from there, right? But often it's hard to leak a pointer and not also crash the program and not actually achieve the result that you want. For example, arbitrary code execution, or like executing like a, what is it called? Executing some shell code or whatever. So this is why ASLR exists, because it requires you, because the address is random, you have to leak the address and then also be able to continue using the program and then use that address that you just gained for some extra knowledge with some exploit script, or I guess doing it by hand, which, yeah, it's a security mitigation. It doesn't prevent the kinds of attacks that it's designed against, but it does like certain kinds of pointer leakage. Like you can still leak pointers, and like your program can just print pointers in certain situations, and if that happens, then you can just use those pointers without consequences if you don't have to force the program really to print the pointers. That's one of the cases where ASLR doesn't really help. But yeah, there's still possibilities, or there's still a lot of things that ASLR makes harder. The same thing, by the way, goes for the kernel. There's also kernel address space layout randomization, KASLR. We have that in Serenity. I think Linux kernel has it as well. So you do the same thing except with kernel code. So if you have control over the kernel, you still don't know where shit is located, because like the kernel is even more well known, I guess, than some random executable. So that's also very nice. So you can also imagine this applying to like an operating system or something.
is what ASLR does. It's something our operating
Also, like high quality animation here I did in Fusion. That it actually, I think it took me like way too long to write this animation. I think it's the first proper animation that we've had so far. Everything else is just in-out transitions, text objects, graphics objects. There's yeah, not a lot of VFX. There's the green screen, obviously, but generally there's not a lot of stuff in here. Just tons of motion, like relatively static motion graphics, which I guess is an oxymoron, but still.
operating system handles automatically. However, for ASLR to work, all the code in our program needs to be independent of the position that it gets loaded at. Absolute addresses can be used, but they have to be fixed by our operating system's dynamic linker right when our program starts.
So dynamic linker is also, yeah, the program from the operating system effectively, or like it's so deep into the operating system that on Linux, like you can't, like even across distros that use different C libraries and different Unix utilities, you still have the exact same dynamic linker because it's so deeply related to the operating system. You just wanna have the same thing that does things in the same way. And that's also like the interpreter field in your ELF executable. Basically, your ELF executable tells the operating system, hey, I'm not just a static executable that you can just execute and like put into memory and run. I need this quote unquote interpreter. I need this dynamic linker. And then the operating system calls the dynamic linker with your executable. And then the dynamic linker goes off and does all of its magic. Like, yeah, fixing like all of the dynamic relocations, and loading, of course, loading libraries, stuff like that. And yeah, that's kind of the thing here. You're learning general operating system stuff here with me. Great shit. I like to be generally educational.
These dynamic relocations make programs larger and slower to start. Getting back on topic, with AUIPC, RISC-V inherently uses addressing relative to the current instruction, which means it's automatically position independent. No relocations, no complicated linker logic, no nothing. How amazing.
Of course, there are still relocations, like as you can see here.
Relocations,
Where the fuck?
which means it's inherently slower to start.
Here we go. Of course, like as you can tell, these are all relocations of the kind that you can't avoid. I don't exactly remember what jump slot does. I tried looking it up because I was curious in the ABI spec. I don't quite recall what it does. Maybe Sönke can enlighten us, because Sönke definitely implemented this one. But yeah, it's these are already like, yeah, relocations that are entirely needed and can't be removed by AUIPC. And if you include, like, if you look at the like static relocations, there's a lot of stuff where program linkage table. Oh my god, I don't know what PLT is. Anyways, we're just going to skip that. Suffice it to say, this is not stuff you can fix with AUIPC. But yeah, there are other things, like there are AUIPC specific relocations basically, but all of those are static. If you look at the .a file, which hasn't been properly linked yet, you will see a lot more relocations, and all of those basically get removed away, and yeah, you don't have anything except for this. Like, I think pretty much the entirety of Serenity libc only has these jump slot relocations. So yeah,
get relative no S tier for our
yeah, and that's of course why AUIPC gets S tier.
AUIPC. Okay, I have to speed this up, but we also have to talk about how jumps work in RISC-V.
Speaking of speaking this up, we're 7 minutes in and I've talked for over an hour. Holy shit. Okay, I'll have to definitely talk less.
First of all jumps are relative, and since JAL also uses that 20-bit immediate, with a bit of math we can calculate the jump range to be plus or minus 524 kilobytes in either direction. Almost correct. Since all instructions are at least 16 bits large, we don't need to specify the lowest bit. It will always be 0. So we double the range.
By the way, here we have the very, very funny J-type immediate that I agree is really, really curious. But like, there is a point. All of these ranges align up with other immediates. This is the thing I showed earlier. Yeah, and of course the jump range
to about 1 megabyte in either.
The jump range is actually plus or minus 1. It's plus or minus 1 megabytes. I didn't use kibibytes and megabytes here. That's something that someone pointed out that is absolutely silly. So yeah, yeah, not write this down anyways.
the direction. That's quite a lot of code. If we're lucky, any function we call will be within that range. This was the boring part of jumps, and all of them work this way, though with different ranges. The interesting part is the and link part.
By the way, if you have something outside of that range, you basically need, well, either you can do a jump and link register, so you like load the absolute address, for example, from like some global table, like the GOT, and then jump, like load it into register the address and then jump to there. Or you can also jump via a trampoline, I think it's called, which means you have some other place in the code, usually between functions, where you jump to, and that one just jumps onwards to the function, which is, yeah, you trampoline off of that single instruction. This is also something that ARM has to do quite a lot, and it sometimes makes linker code, like how linkers have to deal with the code, it's quite complicated. But luckily, nothing we have to deal with for the instruction set itself.
Of jump and link. What are we linking? The return address.
Yeah, I also feel like link is a slightly weird name if you don't know what it's referring to. But I believe ARM is using the same name, but I'm not quite sure. But yeah, this is like some generic term for this, I guess, that hardware people have.
All unconditional jumps store the address of the next instruction into the destination register, and only then jump to the new.
Also, I think from our EPC onwards, I started using like the generic syntax here, like RD instead of a specific register. Like RD is the destination register. It's like any integer register, and offset is just an immediate. In this case, we can read here what it is. So I hope that was relatively clear, but I wanted to specify the general form because it's easier to refer to, I guess, and also easier to reference from my speaking and my text.
Address. You might be familiar with how many architectures push the address of the next instruction to the stack once they perform a function call. But RISC-V never does this automatically. If we store the return address in a known register, the function we just called knows that this register must be retained.
Also, yeah, I misspoke there. I meant to say called. I didn't correct it. I didn't realize it during recording. I just left it in. I didn't even put in like a correction text on top here, which will happen a few times later on. Just said the function we just called. It's a D, not an S. Anyways, it's the first bit of more complicated code. Yeah, so in this case, of course, we're jumping to this function and linking with the RA register, which is X1, which is like the standard ABI register for the return address. And then down here, yeah, we know no matter from where we get called, the RA register always contains the return address. That's why it's called RA, obviously. And yeah, and then we can have function logic. This is just a random instruction. And then we want to return by jumping to RA. I didn't put in the code for doing that because the code for doing that is, of course, jump and link register, which is going to be explained in the next section. I guess I'm also going to put the subtitles up here so you can read the stuff down there.
For the return later on.
Oh, Nico says, I think in ARM it's jump for jumps and call for jump and return register. MIPS has jump and link. Oh, okay. Yeah, I know that MIPS definitely has this. Then I guess it's slightly different than ARM. But I remember, oh well, that's old ARM, right? In old ARM, you can just write to the program counter to change execution because the program counter is a normally accessible general purpose register, which to me is like, it's somewhat of a shit decision in the sense that it makes branching logic in the microarchitecture complicated, but it's also, I think it's just really funny. Yeah, I want to go to this function. Let's just write to the program counter with an add instruction. I love this. This is cool shit. I mean, as you might hear, I'm despite me really loving RISC-V for its openness, I also think that ARM is generally not a bad instruction set. So I'm going to say a lot of positive things about ARM as well. And it calls the return address register LR, the link register. Yeah, so ARM. And also, yeah, branch and link. Yeah, that was what I'm thinking of. So in ARM, it's called branch and link, or at least that's, yeah. At least something similar. Of course, it's not the exact same.
So it can store it on the stack if needed.
Anyways, getting back to this, yeah, you can see, of course, for saving something to the stack, we, of course, first have to increase the stack space. So add 4 to the stack. This is wrong. This should say -4 because the stack grows downwards, of course. I just realized this just now looking at this code that it's wrong. Anyways, and then, of course, you can store to the place you just increased. And also, I guess I didn't point this out ever, but the stack pointer is also just the general purpose register. I think it's X5. I don't actually remember. But yeah, so the stack can be manipulated with normal instructions, which is a pretty standard feature of RISC instruction set, which I didn't talk about. Like MIPS has this, ARM has this, everyone has this. PowerPC probably also has this. Yeah. And yeah, you can see this is, if you put a -4 here, like these two instructions would save that to the stack. If you want to save more stuff to the stack, of course, you can immediately increase the stack pointer by a larger number, and then store all of the stuff with a certain offset from the stack pointer, which is this kind of sequence. Add something to the stack pointer, then a bunch of stores with offsets to the stack pointer. That's basically your initial pushes in the function prologue that you know from other instruction sets. This is something that RISC-V has as well. I guess RISC-V generally needs like one instruction more, right? You need one extra instruction to do the initial offset. But it's, as I've said before, it's not really a problem. There is a specific instruction extension that reduces this to like a few compressed instructions or like a single one, but this is not generally usable. It's for very specific embedded systems. So better get used to this this kind of code here. I mean, this is also like the nice, or the thing with RISC instruction sets in general. You need to know like pseudo instructions and certain common sequences that achieve things that are just a single instruction in CISC instruction sets. Anyways, let me stop rambling
But if
again.
the function never calls another function, then it doesn't even need to do that. Neat optimizations all around.
Yeah,
Of course.
So this is, of course, of course. So this is the main optimization that you can do. And like, I thought this optimization was somewhat hypothetical, and I didn't think like compilers would do it that often. But actually, like, I've looked at some Rust RISC-V code yesterday, and it actually happened there. Like LLVM optimized it in this way and did like tail calls and stuff. So you had like a function that never called another function, or when it called another function, that one also didn't call another function. So it's like in some very specific circumstances, or like even when you have sometimes functions calling each other, if this call chain is very limited and most of it is inline, you can like omit the entire stack manipulation stuff, which is super great. You can just not fucking care, and like at least not push the return address, sometimes even not push like any of the argument registers. There's a lot of, because you have this like limited functionality that's required of you from the instruction set, the compilers can go wild and do whatever optimizations they want, which is also one of the great things you can do with RISC instruction sets. Yeah, so this is not just hypothetical what I just said with the optimizing away the stack push. This is actually that happens in practice on higher optimization levels.
Some jumps are just within a function and don't care about the return address. That's also very easy. We can store the return address into the 0 register, which by definition throws away.
Yeah, 0 or X0, which is the exact same thing. So we're just jumping to the loop here, and we can run some code, and then we have a loop. Yeah. Pretty straightforward code, I hope.
All data and always reads back as 0.
Yeah, so that's the first time I mentioned the 0 register, I guess. But this is also one of the things, right? The ARM has this as well, but I think it's the X31 or R31, like the last register in ARM, I think. So like to have a register that discards all the data and reads back as 0 always, allows you to synthesize so many instructions. It's kind of insane. Like there's so much shit you can do by just having a register that is constant 0. And you need so many fewer instructions. It is probably my favorite thing in the RISC instruction sets that have it in general. Like, I mean, as I said, RISC-V has it, ARM has it, MIPS has it, possibly PowerPC. I always need to mention PowerPC because I have a friend that is all about PowerPC, and I'm actually warming up to PowerPC. I think it's quite nice. And it's also now open, so it's quite a cool thing. Anyways, point being, as constant 0 register, we'll see that a bunch. You can probably think in your head already about multiple ways that you can synthesize cool new functionality from existing instructions with the 0 register.
Overall, JAL goes into S tier, just for the reason of it implementing both function calls as well as an unconditional jump within a function.
Yeah, this is also a criterion for S tier, right? If you have one simple generic instruction that can do multiple things, and ideally all of those things have a clearly identifiable pattern that you can optimize in the microarchitecture. Like that is just genius design. Like it reduces the load on on simple instructions, reduces the load on complex instructions, it reduces the amount of required encoding space. It's just, I love it. It's so good.
We just used JAL to make a function call. How do we return from the function? Easy, with jump and link register. This time the destination is not an immediate offset. It's instead an address stored in a register plus a 12-bit offset.
And as you will find out, like register plus 12-bit immediate offset is like the standard like addressing format, or like pretty much the only addressing format that RISC-V has. This is the same for loads and stores, most loads and stores at least. Yeah, so like the jump range as offset from the register is fairly large. It's 2 kibibytes, but you don't really need that if you can like use a register. And I did on 64-bit, you can then jump anywhere into the 64-bit address space with this.
You all know where this is going. Since we stored the return address in a register, all we need to do to return is to jump and link register with that same register. JLR can also do things like jump tables and any other application where you need.
Yeah, so the jump table code here is something I just came up with on the spot, I guess. I think you can do this a lot, like it's not very optimized. Meanwhile, x86 has more than 3 addressing modes, even on x64. Yeah, it's just, I mean, like there are now instructions in like the B extension set that provide like shorter ways of writing certain common addresses, like for example shifts and adds combined into one, so that for example indexing into 64-bit integer arrays where you need to shift left by 4 for the address first, shift left by 3 the index, and then add that to the base address, stuff like that. Like you can all combine that into one instruction. This is what the ZBA extension does, for example. Like there is some extensions for RISC-V now which basically give you easier ways of generating the addresses, but the addressing modes themselves are intentionally kept super simple. And like in my opinion, it's like either register or register plus offset. Those two are pretty much the only register plus immediate offset. Those are, in my opinion, like the most important addressing modes and generally the only ones you need. And oh yeah, RAX plus 8 LEA RAX, RAX plus 8 RBX. So you have, I think that's the address, the value at the memory address pointed to by RAX plus 8 times RBX, and then load that into RAX again. So you can do something similar to what I just described in RISC-V. You can do that with on x86 immediately in one instruction with like that's just the point, right? CISC instructions have more functionality per instruction, which doesn't mean that those instructions are going to execute at the same speed, or that they're necessarily any better or more flexible because you have more of them. Yeah, anyways, so this is like kind of, yeah, not very well optimized. Like we first load the upper 32 bits of the jump table, then here we have the lower 32 bits of the jump table, and we add to this address of the jump table, which is in S0, we also add the temporary the offset that is in the temporary, and like the order is kind of weird, but we have to do it in this order, of course, because the jump happens here. So yeah. Oh yeah, load effective, sorry, the LEA, which x86 stuff, which I was talking about, load effective address. Yeah, and I know it's not actually a load. I thought it, like, because of the angle brackets, I thought it was then actually a load, but yeah, it's just like address computation stuff. So you can, in x86, you have load effective address, which gives you all the address computation functionality, but you're going to store the address instead of actually loading from it. Store the address in a register instead of, yeah. So yeah, as I was saying, this code somewhat weird. It's the order is kind of fucked, and in general, like you're jumping into the jump table, right? So yeah, depending on what use case you have for this, maybe there's not a use case for this. I just came up with this, and of course over here you can jump to anything in like the first 12 bits of the address space, because you have the not the first, yeah, like signed, you can jump to the first 2 to the power of 11. So what is that? Like the first kibibyte and the last kibibyte of the instruction space, which is super cool because at least sometimes on RISC-V, on some systems at least, you will have the interrupt vector at the 0 address. So I think that's in ARM, but like I would imagine that RISC-V would do something similar, like put something in, put the interrupt vector in the lower addresses, on the very lowest addresses, in a simple architecture, of course, like in microcontroller. So you can immediately jump there if you just want to call some kind of, like, you can basically emulate a software interrupt with that. Or you can have stuff. I mean, in the manual they list examples for, you can have like, yes, common software routines, like stuff stored there. Like you can have very simple library functionality. Like there's a lot of things where this is useful for simple architectures, I guess. Not really useful for complex architectures, but in this case, yeah.
Need a calculation to figure out your destination address. Overall, while it still has multi-purpose application like GEL, I'm only going to give it A tier for its slightly lowered usefulness. It's mostly just used for function returns.
Yeah, that's also kind of my experience. I've not seen it a lot outside of just doing ret, which is GEL 0, 0 in brackets RA. So jump with the offset 0 to the RA register, and it store the next address in the 0 register because you don't care about it. And of course, the other main case is like calling faraway functions. But I guess that's pretty uncommon if you have not terribly humongous, like terribly large binaries with also not a lot of external libraries. Maybe I've just looked at the wrong libraries, I guess.
Okay, so I spend a lot of time on like 4 instructions. Fortunately, there's absolutely no need to talk separately about the next 6 instructions, all of which do essentially the same thing. The branch instructions. Branching, of course, means to jump only when a condition is met, and the conditions we can use are...
So as you saw, like this is still a 12-bit range, but because we're missing the lowest bit now, like before in JAL and JALR, in JALR, actually, we're not missing the lowest bit, so simplify the encoding, but the lowest bit is always masked off by definition. This is one of the many details that I jump over. But like, yeah, JAL also is missing the lowest bit, so you can double the range. The same thing is happening here.
Self-explanatory. Equals, not equals, less than, greater equals, less than with unsigned integers, and greater equals with unsigned integers.
Of course, here's also where the 0 register comes in, because you can you can compare to 0, so you can branch equals 0, branch not equals 0. Very easy to do if by just comparing with the 0 register. You can branch if less than 0, greater than 0, and so on. And also, like, of course, greater than is literally just swapping the operands of less than, and the same thing for a less than or equals. And there's like a bunch of pseudo instructions for doing all of this. So like this is the minimal set pretty much that you would want for any kind of comparison, signed or unsigned, and you can synthesize all of the others from this.
Now you might actually not be surprised to see branching instructions like these if you've never seen any instructions of any instruction set.
I hope this is kind of correct. Like, I feel like these are very intuitive. Like, you do a comparison and then immediately branch, like in the same instruction. This sounds somewhat CISC in the, like, it even sounds somewhat CISC to me. Like this is what a CISC instruction set would do, or some actually do, apart from other things like doing a comparison first and then branching. And of course, in RISC-V, you can still do stuff like the set if less than, which we'll see later, and then branch if equals 0 or not equals 0, which is pretty much the same as like a compare and then the branch. And if you need the compare result later on, then that's something you can do.
They're quite obvious and logical. We take two registers, compare their values according to the conditions, and then jump or not, depending on the condition. However, this behavior is quite unique in RISC-V. Virtually all other instruction sets, even ARM, use flag registers to store the result of a comparison and then branch later on based on that previous comparison. But
I sincerely hope that I didn't fuck up this ARM code. This is based on some vague research I did for like 10 minutes on the internet. How to branch in AH64 Blitz? I need help. I'm stuck in editing hell. So I hope this is like kind of correct code for branching if 1 is not equal 3. So yeah, and like here you can also see load immediate. That's a pseudo instruction. In this case, this would just be add immediate, like this constant 0 register to 1 and store it into S2. So add S2, 0, like written out 0, 1. So yeah, I guess, yeah, and in ARM, I think in ARM this should be roughly the same thing, but they just call everything a move because I guess you can. That's fine by me. Yeah, so as you can see here, you have a comparison like in x86, and then you set the flags. And yeah, flags kind of fucking suck. I hate flags. I absolutely hate flags. Like I think flags only really made sense for 8-bit processors, possibly. And anything beyond that doesn't really need flags. Fight me. Because like we have such an easy time nowadays. We have so many registers. Like all of these instruction sets start out with oh yeah, ARM conditional execution, my beloved. Absolutely. I mean, RISC-V also has it now, but yeah. Yeah, so so yeah, like we have 32 registers in all of these instruction sets by default. Like even x86 like got a bunch of extra registers when moving to 64-bit. ARM always had 32 registers. RISC-V always had 32 registers. Like a Spark even has 128 registers, I think, and you can see like 20 of them or whatever. It's like really, really fun thing that Spark does with like a viewing area of certain registers. You can see like 32 registers ought to be enough for everyone, or rather are the correct amount of registers to have. Oh yeah, I know that like the old ARM versions could have condition codes on all of the instructions, so you can tell every single instruction to execute or not depending on the flags, which is silly. It's like in my opinion, it's wasting a lot of encoding space for something that you're going to not use a lot, even though conditional execution is a useful feature. But yeah, anyways, point being, 32 registers. You can spare one register to store your flags temporarily while you need them. That's the main point here. You have enough registers, you don't need a separate flags register, you generate a quote-unquote flag on the fly, you put it in some random register, you do a branch based on it, you do multiple branches on it or whatever, and then you overwrite it again when you don't need it anymore. It doesn't require your microarchitecture to keep track of a bunch of extra stuff. The problem is also that, yeah, of course, in architectures with flag registers, you have like a lot of stuff that will just set flag registers by default. I think not everything uses it by default. Like not all add instructions on ARM, at least, I think, use the carry flag to like, yeah, add with carry. But like it is almost always set. So you're constantly modifying register state. You constantly have semantic dependencies. Like it just fucks up your pipeline hard. And that's my problem with flags, I guess, mostly. Like it makes it's just kind of like it makes everything more complicated. It makes simple implementations complicated because they have to have like this very special register that has very special stuff. And it makes the hardcore fast implementations complicated because you have a lot of extra dependencies that really should be dropped, or like you can optimize the dependencies away, of course, but you have to spend a lot of extra effort. And the nice thing is if your ISA by default tells you how your like by default like that there is an obvious way to optimize stuff and that you don't have to put in a lot of effort to get like the basic optimizations going, and then you can look into more complex stuff. Like easy code, straightforward code should be easy to optimize, and complicated code should be complicated to optimize. That's kind of the thing, right? I think that makes sense, I hope. Let's continue before I ramble anymore.
Flag registers create several problems that are out of the scope of this video. You'll have to believe me that having no flags in our process is a good thing and another reason to like RISC-V. Anyways, no flags means that the comparison, of course, has to be part of the branch. And it also means S tier for the branch instructions.
After all that I've said there, of course, it's S tier. And by the way, here's the here's the TLDR of this. And yeah, there's like you need somewhat flags, like you have floating point flags in RISC-V as well, because the standard kind of requires it, but those flags are in the CSRs because accessing them is like a thing that you don't need to do that often, so it's like kind of unimportant. And it's also like, I think people would prefer to like turn it off or like have the option of disabling it if it's not needed, but it's like a standards thing. You have to comply to IEEE 754. We'll see a lot of that towards the end of the video. Let's continue.
Let's increase the batch size to 7. Loading and storing
and
to
8,
and from memory is one of the most basic things a processor does, so it's interesting that RISC-V pretty much has only these few instructions to do that. All of them do a different size, 8 bits, 16 bits, or 32 bits.
So yeah, RISC-V always calls 32 bits a word because the basic instructions are that size. Even on 64 bits, 32 bits is still a word because it's also the the smallest granule of alignment. I think there's like there's like with atomics, this is the smallest alignment thing that you need to be able to do. Anyways, this is like always tripping up people that come from x86 and expecting that 16 bits is what is called a word. Like I even had a professor once, like not a computer science professor, but a professor calling 16 bits a word unconditionally, like in general, and that is not true. 16 bits is 16 bits or 2 bytes, and depending on what architecture you're talking about, it might be called a word, might be called a half word, it might be called something else entirely. Like usually a word is like your pointer size, but not always. Like word is pretty arbitrary of a term, at least nowadays. And that comes back to, do we call an architecture Like what bit size do we give an architecture with, for example, 8-bit registers, but a 16-bit or 24-bit bus and stuff like that. Like it gets really complicated, or with like much larger internal register for scientific calculations, but a much smaller bus. That happens on some weird supercomputers. Like there's a lot of nuance here. You just have to define your architecture where you specify which word you're talking about. Probably meant a word in the sense of a 16-bit quantized large language model token. And no, actually, it was specifically in reference to, yeah, I mean, I know you're joking. It was specifically in reference to the, to like, yeah, low-level computer hardware stuff. So, yeah, here are the names, of course. D for double word is going to come up later for 64 bits, and Q for quad word for 128 bits is also something RISC-V specific.
And some can turn off the sign extension, which is neat. All of them address memory.
So yeah, by default, if you load, of course, the value that gets loaded is sign extended, and you can turn that off.
Via a register plus a constant offset, which is useful for object field accesses and getting to any 32-bit offset together with AUIPC, for
We saw this kind of code before.
If you have ever seen any CISC instruction set, you might be surprised that no other instruction accesses memory. This is because RISC...
This I copied from Godbolt to be absolutely sure. This is like, I just typed in some C code like int, like some integer pointer plus equals 3 or whatever. And then it spits out this. I guess you can leave out the keyword printer depending on your syntax, but yeah. So in x86 you can immediately tell the machine, please add to this memory, not to RAX, but to the memory pointed to by RAX.
RISC-V is a so-called load store architecture, just like ARM. There are instructions for loading and storing values, these 7, and there are instructions...
And not just ARM, by the way. I'm not sure if like this is a defining feature of RISC. I haven't researched that, but I'm pretty sure that almost all RISC architectures are load store architecture, because this is like a major thing that simplifies the instruction set a lot.
For doing calculations on the values, which we'll see later. And the two kinds of instructions do not intersect.
And this also, like, I mean, if you also look at like newer x86 stuff, like the vector extensions, for example, I'm pretty sure that like AVX and whatever are also load store architecture. So like everything is tending towards this design because it's generally considered a good design, because you can have a clear distinction between, okay, this stuff needs to go into the memory execution unit, this stuff can go into an ALU unit or a floating point unit, and that like, yeah, that, as you can see, I'm talking about execution units, I'm talking about super scalar out of order execution. Like you can do a lot of really fast stuff with load store architectures.
There's no way of both loading a value from memory and also adding it to a value in a register in the same instruction. Load store architectures are quite neat, but people have known that.
Yeah, and this is like common, like this is common knowledge. I think at least since I would say 80s, 90s, people knew this was the way forward. And that's generally the thing with RISC, right? Before that, people were just making stuff that was kind of fast in the moment because optimizing microarchitectures was complicated. And then they figured out, okay, well, we can simplify the instruction set down and then do more and more optimizations in the microarchitectures. We can do pipelining, we can do branch prediction, and so on and so forth. So that's kind of where the entire RISC idea also comes from, even though like it's mixed up a lot in modern architectures. There's like different RISC and CISC aspects in like even something ARM, probably best example. But yeah, it's just this is common knowledge. I'm not telling you anything new. RISC-V is not telling us a lot of new things. Like there's just so many things that already existed, and this is just putting them all into one nice package that is open source.
Lots of architectures do what RISC-V does here. It's neither unique nor mind-blowing. Still useful though.
That's why I'm giving it only B tier.
Do you still remember Louis and AUIPC? Well, here finally comes the instruction that we need.
The order is kind of weird.
Adding the lower 12 bits to that register. or any immediate to any register, really. This is the perfect time to mention that RISC-V almost never overrides one of the source registers with a result. In this case, we can take a value from a register and add the immediate to it, but store that into a different register. Very useful if we need the original later. ADI on its own would only deserve B tier, but it needs to be bumped up for one simple reason. What happens if you add any register to any?
I think this might have been the point where I had to switch my teleprompter setup, and the teleprompter is running slightly slower. So like my speaking rate is slightly lower than earlier on. It's kind of weird. I still need to figure out what the optimal reading speed is, or like it really depends on the video. I'm always figuring it out on the fly. I have like 30 minutes of footage, or like multiple hours of footage before this, where I'm just figuring out stuff, like doing trial runs of the early parts of the script, figuring out the proper speed for me to speak at. Yeah. You can see here a bunch of add instructions that do absolutely fucking nothing.
Immediate and store it in the 0 register. Exactly.
Nothing.
It's a no-op. So naturally, we don't need a separate encoding for an op, as we can just use any of the literal thousands of ADI instructions that don't do anything. For complicated practical reasons, we only use one of them, but still.
And also, by the way, not just ADI, but a bunch of other instructions, of course, also have certain things with certain registers, like the 0 register, where they don't do anything. So there's a lots of knobs. Actually, I think I might want to show you the knob encoding, if I can. Yeah, I can quickly find it. Where do we have the hint stuff? Oh yeah, okay, I found it. Found it. Wrong screen. Here we go. So yeah, all of these knobs are also hints, as we'll hear in the video in just a moment. But yeah, this is the one that we're talking about right now. But there's a lot of other ones, usually with a destination register of 0. And like you can see that the number is quite large. Like some of them here are already taken up. This is like temporal locality hints. We have the pause one here, which will come up in the video. Like there is a lot of options of doing like a lot of hint stuff, and I don't actually. Yeah, there is some custom use. They reserved like a lot of stuff for standard use and not a lot of stuff for custom use. But I guess it's fine if you have like specific requirements. You can put them in here. It will probably be enough. I think, yeah, some of them are taken up by something else as well. So I feel like the space for standard use should have been slightly smaller, but I guess it's fine. Anyways, let us continue.
Even useless instructions are useful in RISC-V, A tier. I had some trouble deciding what to do with those two. Set less than immediate is intuitive in what it does, but a bit mysterious in its purpose if you ask me. It compares the register operand to the immediate and sets the result to 1 if the register was less than the immediate and 0 otherwise. Same thing with unsigned comparison.
And of course, this is quite obviously, you can do this very easily with the carry flag from the ALU. So computing this is just a subtraction, or yeah, it's very cheap. So that's not the part that troubled me, at least.
In SLTIU, of course. This appears to be useful for comparisons for other purposes than branches, including, for example, composing comparisons into complicated conditions before actually branching, but it still feels evasive to me. I found it somewhat hard to read assembly code.
Okay, I'm looking through Discord right now because Sönke had a really nice explanation of, yeah, SLT is quite useful. You can even make a set equals 0 out of it with SLTIU, temporary, or the register 1. So so you can set the register if it is equal to 0. So you can do a set less than immediate unsigned. So if the unsigned is smaller than 1, so if it is 0, then you have a set if equal to 0. And yeah, it's easy to implement. So yeah, there's some uses to it. I guess I was just wrong. I found this random piece of code here. I mean, this, or I think one of the other use cases, I guess, that I was saying. Yeah, in general, it's nice for branches programming. Yeah, that's absolutely valid. Like also, for example, you can do array bounds checks with it. So if you have a either static or non-static array bound, you can set a flag in a register, so set a register to 1 if the array is in bounds. So I guess you can like probably do stuff with that, but I mean you can also just branch based on whether you are within an array bound or not. So yeah, I agree. It's I guess I'm not smart enough to really understand all the nuances here, all the possible use cases, but it does make sense that it's useful for branchless programming, even if I can't tell you the details here. But like in this case, this looks like an array bound to me. Don't know. I think I took this from some libaudio code. Like this should be some FLAC code or whatever, because I always use FLAC code as examples, obviously.
Containing SLTI and SLTIU, but since there's a lot of that, they're clearly useful for compilers. D tier for the missing or poorly explained rationale.
Yeah, I should have probably given it B tier, like given it the same tier, maybe even the same tier as the conditional instruction that we will see later on, because it's like branchless programming stuff, of course, very important. Make the basic blocks larger, take the pressure off of the branch predictor, always important.
If you already know the instruction list, hold up, there is a reason why I am splitting XORi from the other two. Again, on the surface, this is just the instruction for bitwise exclusive OR, XOR, between an immediate and a register, really nothing special. However, since the 12-bit immediate is sign extended, this means that we can easily XOR a register with all ones.
And of course, the sign extension also goes for and OR, and like this goes in general. So even for instructions where sign extension doesn't seem logical, like the literal logical instructions, it's still applied because it's just the general case. And as you can see with XORi, it actually has a practical purpose for inverting, like bitwise inversion of a number.
By just using the immediate hexadecimal FFF. And if you know anything about XOR, you know that this will flip all of the bits of the operand. A logical knot. Absolutely no need to use a separate instruction here. A tier for XORi. ORi and I aren't special, as you may imagine. Simply a bitwise and or with a 12-bit immediate. That part is quite limiting. They are still useful, don't get me wrong, but not much in comparison. C tier. Last of the immediate instructions, shifts. Of course, they're pretty darn useful. I would estimate that most shift amounts are constant, and 12 bits is more than enough for the 6 bits we need for even a...
Yeah, this is like for 32 bits is 5 bit, for 64 bits is 6 bits of shift that you need. But this is like the only case where the immediate can actually encode like the entire second operand, because it's only that small, which is of course extremely useful. If you have any kind of shift with a constant in your code, it's gonna be this instruction, and makes things super simple. Versus, of course, if you have some kind of large addition or large subtraction, even if it's a constant, you might have to have multi-instruction sequences, as we saw before. And yeah, logical arithmetic shift, I hope you're familiar with the concept there. That like arithmetic shift sign extends, so you have a division by 2, and logical shift doesn't sign extend. And of course, for left shift, it's both the same.
64-bit shift. What's also quite neat is that some of the extra 6 bits of available space is used to differentiate between logical and arithmetic right shift. Solid A tier.
Of course, the rotation instructions aren't in here. They are in the B extension. But like, I mean, in general, rotation is fairly rare. There's like very specific circumstances where you need rotation, and like shifts you constantly need. So it makes sense that there's no rotate in the base ISA.
I'm pretty sure I can hear quite a few of you shouting for a while now through the screen. Yes, that really works. Where's the add instruction? Here it is. As I've said before,
I haven't actually. I'm going to check right now, but I don't think anyone actually skipped ahead to the add instruction. I'm going to check the. Where is that? That's at 1622. No, there is no, but people even jumped away at that point, like, or jumped ahead to like the large memory model section. Nobody jumped ahead to like see where's the add instruction. What ranking am I going to give the fucking add instruction? Luckily, nobody did that.
Our register instructions in RISC-V always use 3 registers, 2 operands, and
yeah, this
one
is also very
destination,
normal, of
which
course.
makes a lot of operations easier without requiring additional moves. Additionally, sub serves as a negation instruction since we can just subtract any register from the 0 register.
Once again,
Even so, these instructions are pretty boring and basic, so they get B tier. From now on, the instruction listing order gets kind of weird.
I mean, it
so we
already
have the logical shift.
It already was kind of weird, but it's getting even weirder now. And at the floating point extension, I just gave up because I didn't want the video to get a lot longer because I have to spend like one sentence on every single instruction. Even that was kind of too much towards the end. Like floating point starts here, so like floating point is still 7 minutes or so. So yeah.
Left instruction all on its own over here. I gave the immediate shift instructions A tier for the usefulness of constant shift offsets, and equally, I think the register versions are a little less important, so they belong in B tier. Once again, here are the set less than instructions, now as register versions. Still D tier, even if they are more useful than the immediate versions. As we saw previously, XRI is more useful.
Maybe you've noticed, but like I've shortened the interludes also a bit. Like some of the instructions that have very short descriptions have shorter interludes than the long ones, and like the longest interludes are used for the full extensions. They actually, yeah, they're slightly differently programmed, so to speak. But like the animation here is always the same. I just copy pasted the same text object with the same keyframes. I just changed the text.
Useful than it may seem. That is not true for XOR. It's just as useful as an XOR operation is in general. So not a lot, but also not useless. C tier. As I said, register shifts belong in B tier.
This like, I think this is the first time when I left the background music running because it was literally one sentence. I was thinking, okay, I could, like normally I have like a few seconds of audio of background music still playing after the transition, and then I have a exactly 2 second fade off, usually so that the first 1.5 sentences or so are included. But in this case, there is only one sentence, so it wouldn't have, like I would have needed to fade it off immediately and then fade in the next or have the next drop there. So I just skipped it in that case. So you can have this kind of nice transition here.
As I said, register.
Also, this track is fire.
Belong in B tier.
Good music.
The 2 remaining logical instructions go to C tier, like their immediate counterparts.
In this case, I faded it off because I had a very different instruction here, so I wanted to have a different background music. And I mean, in some cases, I actually reused specific tracks for specific topics. Like I think I used the same BGM for all of the memory model stuff. And so, I did reuse some for like all of the arithmetic stuff, I think, but like only slightly, because in the end I just wanted to have a bunch of different tracks, and like as you can see, the track list is quite long. So yeah.
We're almost at the end of the base instruction set, and fence is the first instruction relating to system operations that we can do in normal applications. As the name implies, fence is responsible for memory fences. Most of you probably aren't fully aware of what that means. So
I mean, most of you watching the stream are probably aware but I'm going to give the most terrible explanation of the RISC-V weak memory model now. So guess that's fun. I mean, everybody who has written, like, at least in C++, like atomics, low-level atomics code, you've dealt with fences for sure.
Let's try getting an idea of some of the most complicated things in the RISC-V ISA. Memory models. The memory model is the formalized model of the order of loads and stores issued from a certain processor and how that order is observed by all other processors. It is most relevant for any multiprocessor system with complex memory mapped I/O.
Yeah, this is like this kind of explanation isn't even in like the explanatory model part of the RISC-V spec or anywhere else on the internet. I think I somewhat stole it from like I found a good book which explains mostly total store ordering and like x86 and Spark, which have total store ordering and how it's different from store what is it called? Sorry, sequential consistency, which is the strongest one. That's like I actually did do a bunch of reading on this kind of stuff to actually get like a good grasp on it. I still don't feel like I understand it very well, but like I also skip over all of the details here, so don't expect me to give a good explanation of the memory model like now and in the director's commentary. But yeah, this is like the best explanation I could find. Like formally, you don't talk about execution order. You don't talk about stores or loads to be committing. You talk about a more formal notion of like visibility of stuff and like preserved program order, and like there is so much complicated shit that I just leave out. If you're actually interested in it, go read the spec. As Sönke just says, the RVMO, so RISC-V weak memory model, explanatory material is still a lot nicer than the one from the ARM manual, from the ARM. Yeah, probably. I mean, they have like three main sections. They have the first one, which gives you the axioms, which are formulated in plain text, which are basically the formal, but in like a math proof way, right? It's like a written math proof, basically, of this is what the memory model has to look like. Then there is the first appendix, which gives you the explanatory material. And then there's the second appendix, which gives the formal model written in some formal specification language. So actually the RISC-V memory model has like formal specifications in like specific languages in it and like proof checkers, and like there's so much formalism behind it. I'm pretty sure this is one of the most rigorously specified and tested memory models on the planet. I'm pretty certain, which is also really nice because it gives zero ambiguity when an implementer fucks up and we have to tell them you fucked up. We can tell you right here you're violating this and that rule. Yeah. Gotta run, pick up the kids. Thanks for the stream. Thank you, Nico, for coming over. I guess if you're in the States, then yes, it should be around noon right now. So see you.
Where there is multiple devices accessing memory at the same time with possibly unpredictable timing between them. RISC-V has almost 100 pages and 3 chapters in the specification dedicated just to the memory model. So forgive me for giving a really fucking simplified explanation here. Very important, the memory access order can be observed differently from different processors, and multiple different orders are all allowed. This
is like the main thing, right? Just because I see certain execution order, just because I execute code in a certain way, doesn't mean that that everybody else has to see that in the same way. And this is also true to some degree on x86, but it's true to a much lesser degree because x86 has effectively total store ordering, which I'm going to explain in a moment.
Allows a processor to use caching and out-of-order execution to run code faster. However, this also means that some really surprising things can happen, like certain addresses in memory yielding different results for different processors.
Yeah, so the main thing is like with total store ordering, it makes like store buffers and store forwarding really simple. But like with the weak memory model, you can do really fucky things in your store buffer, because like the different stores to the different addresses can be reordered depending on what the cache lines are doing. Like if one cache line is currently not available or just being loaded from memory because it's the cache miss, you can postpone that one store, but you can also already commit another store because the cache line is already available, stuff like that, which is probably somewhat possible on x86, but not to that degree. At least I would be surprised.
And non-determinism in general. The more this can happen, the weaker.
At least not on shared caches. It's probably possible on like your own private caches, like L1 cache, but as soon as you get to like shared L2 or at least L3 cache, it's not going to be possible on x86.
The memory model is, but the faster the processor can theoretically be. Looking at x86, it uses a fairly strong memory model called total store ordering.
The total store order should even be a bit further over here, but the text wouldn't fit, so that's what I did.
Which basically requires that all stores performed by a processor always appear in the program order. But processors can still load outdated values if they haven't seen a store yet. While TSO is not the strongest memory model, that would be sequential consistency, RISC-V uses a far weaker memory model that's almost like release consistency. In this model, the rules mainly say what order the accesses to the same memory location.
By the way, I don't know why it's called release consistency, but I guess that's a name that applies here. Like, I don't know how it relates to the concept of like release semantics for atomic accesses and stuff. I can't really figure out the correlation there. Anyways, they say it's roughly release consistency with some modifications, so I believe them. I think the main modifications are like very specific details of like alignment stuff and specific atomic instructions that have certain behaviors that are like, that's just stuff that doesn't exist in like the general release consistency model, because all of those three models that are listed up here are extremely general models that are very architecture independent. And for any specific architecture, there's always going to be special cases and deviations, like for RISC-V in this case.
By the same processor have to appear in. Obviously, it's the same order as the program itself, but for unrelated memory locations, basically anything goes.
So yeah, this is my rough interpretation, and maybe Sönke can correct me if I'm wrong here, but I believe if you have unrelated memory locations, order is arbitrary. If you have related memory locations, and if you have semantic dependency, like dependencies inside of the instructions where like you do an add and then you process that register further and then you use the register again and so on and so forth, these kinds of chains, you have dependencies. That's like syntactic dependency that sometimes occurs in the spec. If you read it, it says it carries a syntactic dependency from this input to that output. That's basically for determining where those relations are. And if you have either that relation or if you have the same memory address, then basically you have total store ordering within the same memory address. And the loads can still be somewhat outdated, but like within some limits. I don't know quite how that works there, but like you can, I now like to think, and I haven't been proven wrong so far, I like to think of the RISC-V memory model as total store ordering, but on the level of a single address. So within one address, there is total store ordering, and between addresses, there is no ordering. And that's probably wrong, but it gives me a good working mental model.
Sometimes this creates problems. In complex synchronization situations, we may be dealing with more than one shared memory location.
Yeah, and this is not just an abstract problem, right? Code has been written for the past few decades, just assuming total store ordering. So assuming x86. And there's a lot of fucky atomics code that is just strictly wrong. It is actually wrong, and they're just relying, like it is wrong according to C++ semantics, for example, which don't prescribe total store ordering. It is literally against the standard. It is, or against the standard in the sense that this program is allowed to exhibit undefined behavior, for example, if we're talking about C and C++. It's literally wrong, but on x86, because of how the memory model works, it will always be defined behavior. It will always behave correctly. And this is a big problem that came up with like the newer, weaker memory models, especially with ARM immediately. I think that was the first one where this really came up. And this is also why like RISC-V has fenced TSO. RISC-V has an extension for enabling TSO globally. Like ARM, especially like Apple Silicon has some extensions for like enforcing TSO, so that you can easily run x86 code under Rosetta without a bunch of extra. So you have some hardware support there, right? So this is like a huge problem. And it's also a huge problem for ARM, not just for RISC-V, because ARM has a very similar weak memory model. This is slowly changing, but you still have a lot of fuckery that's going on where people are just literally, they don't fucking know what the hell they are doing, and just writing code assuming that everything is sequential on both cores. No, it's not. Use your memory barrier. Like the main rule is, right, use your memory barriers, use your acquire and release semantics properly. Like when you use a cast, you specify the memory order properly. It's not very hard. Ideally, you don't write that kind of code. I've written that kind of code with a lot of bugs, but yeah, like don't assume that anything is in any order. It is generally a good assumption that anything can be in any, like the order can be pretty much arbitrary, no matter what you actually write.
Here's where we finally get back to our topic. Fences allow us to limit reordering of loads and stores across them. The instructions literally cannot jump over the fence.
I like the name fence.
There are several options for what accesses we want to limit and in which direction, which will give us things like acquire or release fences.
So yeah, I'm not sure if these are correct. I think acquire fence should actually be RW and release fence should be WRW. I think. But I'm not sure. I'm not quite sure. I'm just sure about the sequential consistency fence, obviously. And also the thing with like I/O is RISC-V basically allows you to define certain memory regions as I/O regions, so as memory mapped I/O regions, for example, for PCIe devices. So you can have separate ordering constraints applied to those versus other regions. And that depends on your specific hardware, your specific system. So you basically just have these two broad categories of memory that you can apply ordering to separately. And yeah, you always have ordering like before, so everything before it has to, like if I have a fence with a prior read fence, then a prior read condition, then that means that all the reads that are before the fence in the program actually have to appear to execute before the fence. That's roughly the idea. Oh, so you talked about the acquire and release stuff on the Discord, I guess. Handy and Sönke, the day before this video came out. Okay. Yeah, I'm really not sure. Like I looked at, I think I found something in the explanatory model or in the comparison to other architectures where there was like a software porting guide and they specified like acquire and release fences in other architectures and how they translate to RISC-V. I think that's where I saw that, but yeah.
Fence.tso is a special case that will give us exactly total store ordering across this fence, which can be used to emulate total store ordering for compatibility with x86 software. Overall, these instructions...
Yeah, throwing stuff against Godbolt always helps. And yeah, fence TSO, by the way, is pretty much just a special case of a sequential consistency fence. Or it is also encoded partially as a sequential consistency fence because it is legal to execute it as a sequential consistency fence. Which of course is stricter than TSO, but it's still, yeah, something possible that you can do. I mean, your specific architecture could be, your specific RISC-V processor could be total store ordering. It could be sequentially consistent, whatever. Doesn't matter. Those are all legal. Those are all stronger. You can always strengthen your memory model. You're not allowed to weaken it, but you're allowed to strengthen it. and they give like a bunch of examples of things that implementations can do in the specification. And yeah, some of those are, for example, just run everything under TSO, basically x86. Yeah.
Instructions deserve A tier because the RISC-V weak memory model makes it super easy to create fast hardware while not making concurrent programming too complex to think about.
Yeah, I hope, by the way, you're all drinking enough. I'm definitely drinking enough. I have a bottle of Club Mate here to stay focused for the next half of the video.
Okay, that memory model section was probably a lot to take.
Oh, there's an editing bug here. Didn't even notice.
Okay.
Yeah, I appear like a few frames too early. Like the background should have already disappeared. Yeah, this is an editing bug. Anyways.
That memory model section was probably a lot to take in. Let's relax and get deeper into system software.
Also, as you probably know, this is like the video segment I jokingly stabilized for like a meme on Fiddy. Let me find that real quick. Where do we have it? Here we go. Have to. My God, there's something really broken about chaos.social. And yeah, I always have to fix the URL.
Okay, that memory model section was probably a lot to take in. Let's relax and get deeper into system software.
I basically did an image stabilization on my head to show Anna like the kinds of things you can do with DaVinci Resolve, and I found it so funny that I rendered it and posted it on Fiddy. So this is where that section comes from, pretty much unchanged in the final cut.
Obviously, most software running on a system has some level of software below it. Below the application is the operating system. Below the operating system is the firmware. Below the firmware is the Intel Management Engine. Just kidding, no IME on RISC-V. Yet.
Intel is inside your firmware. And they're probably doing a bunch of nasty stuff in there. Anyways, it's always important to make jokes about the IME being a government-mandated Big Brother backdoor in your firmware, because that's the fact of the matter, and we will not stop complaining until it is removed. Yeah, so let's wait on Intel to implement RISC-V, and maybe they're going to put IME into their RISC-V processors as well. Well, there might be a BMC coming at some point for RISC-V, or from Intel that is written in RISC-V. Also, Wake on LAN causes some weird ordering stuff. I don't know about that, but yeah. So was the BMC in reference to like a RISC-V BMC or a BMC for other RISC-V systems? Oh yeah, I mean like BMC in general is not a problem. BMC is something you want for servers because you want to have a remote KVM, you want to have remote management capabilities. But that's like all stuff you control, right? You want to do the remote management, not Intel, not the vendor. I do the remote management. That's just, yeah, a normal thing on servers, right? I'm not talking about BMCs. I'm talking about specifically the thing that lives inside your processor that is extremely unchecked, which is the fucky part.
Some functionality is not immediately accessible to us, like opening a file or talking to the network.
Of course, this also is the most simplified stack of software that I have ever made. BMCs for large computers, which are like another computer which spins up your CPU as well. Yeah, that's what a board management controller. That's, yeah, it's like, it's a hey bro, I liked you, I heard you like computers, so I put a computer in your computer so you can computer while you computer. So yeah, I think mostly it's tiny ARM processor, but it's like, it's a fairly powerful processor that is also running while the system is powered off and powers on automatically. And like the main thing, or the main thing I know it being used for is like you can remotely power cycle your machine. And you can get a remote KVM if your SSH breaks or whatever. Like it's much harder to break the BMC than your main system. So you can use it for remote recovery and stuff like that. So yeah, there is a lot of reasons why you want a BMC in a server. And it's really cool. You can also build your own with like a Raspberry Pi or whatever. In fact, below my table right now is like a 2013 Intel server with like dual core Xeons, and it also has a BMC, and you can even extend it to make it even more powerful. It has like its own networking port. It talks to you over serial, it provides a graphics interface for the main system. Like, yeah, a lot of stuff, cool stuff in the server space. Anyways, let's continue with the video.
So we need to ask the software below us to do it. When going from applications to the operating system, we call this a system call. This even goes for operating systems which need to ask the firmware to do certain low-level tasks from time to time, even if it's mostly necessary during boot.
Yeah, so the SPI, as we can see here, this is like the basic interface you have on RISC-V for talking to the firmware from the kernel. And it has a bunch of extensions, but it gives you like debug prints and like talking to other processors and waking them up, like inter-process communication, like the physical hearts, physical processors, and also gives you like shutdown, reboot, and stuff like that. And of course, UEFI is like the main firmware interface you have on your x86 machine right now, but also it will probably become the standard, at least on desktop RISC-V. Hopefully not with ACPI, but with device trees. I hate ACPI so much. Anyways.
And not so much later on. RISC-V provides a unified way of calling into the execution environment by means of the environment call instruction.
Yeah, so eCall is like the very basic mechanism that makes all of these things possible. And of course, SPI and UEFI and syscalls, as you'll see in a minute, all built on top of eCall. So we're talking like absolute basics right now, just software interrupts effectively. This is what, like, if you're familiar with the concept, that's also how you can think about it.
Is actually quite unique. I don't know of any.
Like RISC-V also has this concept. The reason why it's called environment call is because RISC-V has the concept of the execution environment interface, the EEI, which is the generic term for any interface to your lower level. So the EEI from like to your operating system is like the syscall interface in general, like the POSIX specification, for example. Well, the BRS spec is almost ratified with which requires ACPI. Yeah, okay. Oh god. Well, maybe we're going to have to put up with ACPI for another 50 or 100 years, I guess. This sucks. I hate ACPI. It's so fucky. It's just, yeah, another time. Discussion for another time. Anyways, what I wanted to say is, yeah, you can have like the like POSIX or the system call interface. That's an EEI. Like SPI, the SPI is also an EEI. And there's like a lot more specific interfaces on like your specific hardware and like hypervisor stuff and whatever the fuck you can come up with. There's a lot of those. So yeah, this is like a generic term that pops up throughout the spec.
Any other ISA that uses a single instruction for all of its different environment calls. How we actually pass data between the upper and lower levels is up to our software stack. So eCall is both very simple and very powerful. Immediate A tier for this obviously great design.
Obviously, you pretty much do it like normal. You put your stuff in some registers and then you call that. Like in SPI, for example, I think A6 and A7 are used for like the extension that you want to call into and the function in that extension, and then you can use A0 through A5 for like 6 different arguments. So yeah. Here we go.
The next instruction caller is a different story. I once again really don't understand why it exists. I mean, it does have a purpose, debugger breakpoints. eBreak is nothing more than a hardware breakpoint that returns execution to the debugger. Maybe I'm too stupid to understand how hardware debugging is implemented, and maybe I should read the RISC-V debugging specification. But I don't understand why this cannot be encoded in one of the many available knobs and needs its own special trapping instruction. C tier, I guess.
Yeah, okay, so this is like a thing that I'm just too stupid about, I guess. Yeah, the amount of hardware breakpoints is like Sönke pointed out, eBreak is useful because you only have a limited count of hardware breakpoints, and hardware breakpoints are optional. And also someone wrote in the comments, eBreak not equals knob might be a matter of intent. Hardware breakpoints are often not emitted by the compiler, but instead by the environment. Yeah, VM host injecting eBreak into the instruction stream or the hardware itself. Yeah, where a pin that when asserted causes the bus to only read eBreak. Keeping this apart from knob is much more likely to emit nonsensical adds than encodings that are this rare. Yeah, and also, yeah, eBreak is encoded as a system instruction. Like, that's true. It's not exactly wasting space terribly much. But yeah, it's like, I guess it just feels lonely to me, because eCall is quite obvious. You need some kind of software interrupt, right? But then you have like a second software interrupt that's like the other more different software interrupt, I guess. But yeah, there's some use cases. It's like I can't really wrap my head around. It feels to me still like something that like the debugger or the environment would like inject, and not something that you would actually have in the code a lot of the time physically. So if you're thinking you're debugging existing application and you want to have a breakpoint at some place, then you can't really put an eBreak in there, because then you would move all the code around, and that just doesn't work. So yeah, that's the way I'm thinking about it. Anyways, let's continue with 64-bit instructions now. I'm probably not going to say a lot about these because they're, straightforward.
What we saw before is all valid for 32-bit and 6.
Oh, Sönke also said, debuggers typically poke the executable memory and write breakpoint instructions there. Yes, that's what I'm saying, but then you have to shift all of the other instructions that come after it. So, yeah, that's like, okay, I guess you can replace instructions with it, but then you're losing an instruction, or you have to do something where you execute the same instruction twice, and it gets rewritten to the old value or whatever. Like, okay, I just don't understand this. This is, yeah. I guess it's really, like, there really is a reason. No, you poke in place. What do you mean you poke in place? Like, if my oh wait, because eBreak causes a synchronous trap, so it doesn't advance the program counter, so it will run the same instruction again after the trap exits. I guess that's the thing. Yeah, okay. So I guess that makes sense. So you can run the same instruction again, but on the second time around, it's no longer an eBreak. Yeah, okay. Yeah, okay. Let's focus on 64 bits.
64-bit RISC-V. But when going to 64 bits, some extra operations are required, which we'll cover here. LD and SD allow us to load and store.
I basically already explained this earlier.
64-bit values, which is obviously only necessary for 64-bit register widths. Equally, LWU provides unsigned 32-bit load to avoid the sign extension from LW on 64-bit. Pretty obvious.
Yeah, and that's also why we don't need LWU on 32-bit, because like there can't be any sign extension past the 31st bit on 32-bit.
Again, there's nothing special here, just necessary instructions that make sense. C tier.
Didn't want to give them B tier because like the normal loads and stores are already in B tier. That's why they get C tier.
All the normal integer operations use the full register size, so 64-bit for RV64. But
this is also something that is different from other instruction sets where like the instructions keep their original semantics. So like The original instructions would have kept their 32-bit semantics on 64-bit RISC-V, but that's not how that works, or that's not how it works here. I think that's how it works in MIPS, but it doesn't work like that in here. Like, you move the semantics to 64 bits, basically. You change the semantics entirely, because it doesn't really make sense to like have this backwards compatibility, because you're going to have very different stuff anyways, running different software, need to switch the mode of operation of the CPU anyways. Like, it's not really necessary. Like, you can have a processor that supports both, but you need to switch it effectively. And this is also like accounted for in the privileged CSRs. You can switch between 32 and 64-bit mode for certain code, and yeah. And of course, because most of the basic instructions are valid in both modes, it's very easy to like continue executing code after you've changed the CSR and not immediately execute an illegal instruction. Oh, hi. Flag episode 3 when? For when posting, you are now required to make flag episode 3 for me. And just kidding. I have actually animated. I've written 80% of it, animated about 50% of it. I just haven't continued doing that for like a couple of years now. So let's see. I'm definitely not going to finish it before this year's Summer of Math exposition. I'll see if I hope I will have some more time to do YouTube stuff next semester, but we'll have to see. So yeah, right now we're looking at this, of course.
Operations on 32-bit values are still super common, and when we consider overflows and sign extension, the semantics are different enough that 32-bit arithmetic would quickly become complicated on 64-bit. Therefore, all the relevant integer operations get a...
Like, for example, if you have a load word, you load something, it gets sign extended, so the upper, but you have like a 1 in the 31st bit. All the upper 32 bits are 1s because it's sign extended. And then you do a shift arithmetic right. And then you, of course, don't immediately get new 0 bits that get shifted in as you would on 32-bit. You get all of the other 1 bits that get shifted in first, right? So that's one of the problems, for example, with the sign extension and the shifting. Also, yeah, I was thanked for answering. Yes, of course. Yeah, I'm gonna get to it eventually. I'll have to rewrite a bunch of the existing code because Manim changed some stuff, which is kind of annoying. But yeah, I'll get to it eventually. I did do a bit of porting work at GPN earlier this year.
A 32-bit variant that retains the 32-bit semantics. Very useful, unfortunately a bit boring. C tier again. We're finally done with the base ISA and continue with some small
yeah, and that already was 64-bit. You can see it's like very, very short. It's like 2.5 minutes, not even 2.5 minutes. Yeah, so we will go with pause.
Outside of the G listing before continuing later on. The CI hint pause extension defines a simple pause instruction, which previously was a no-op fence. However, now it becomes a basic waiting instruction that tells the system...
I think I also said it's becomes or something there. Very fucky. Also, yeah, because you don't have a second W here, this is a no-op. This doesn't really do anything. I'm again not 100% sure why. I don't fully understand this, but I'm just going to take the specifications word for it that this was a no-op fence before.
System that we're waiting on some condition to become true, like some memory written by another processor or an external device operation. While we could make such waiting super precise, telling the processor exactly what we're waiting on and for how long, in many cases this simple pause instruction is enough. There are several optimizations possible with pauses. We could slow down the processor for some period of time after each pause, We could even stop it temporarily. We could execute some other code instead. All neat things that will increase efficiency or power consumption. However, since this instruction...
The thing is, I think because the specification is so vague, is pause useful for, I don't know, cheat engine? Probably not. I don't think what it would help you with, like injecting code into another process, which is pretty much what cheat engine does, or changing memory of another process. No, the thing is, because the specification is so vague about what pause is allowed to do, I'm pretty sure a valid implementation is just to literally ignore it and basically have the base behavior. So in effect, every single processor that implements the fences also implements ZI and pause, I think. But I'm not sure if that's actually correct interpretation. I mean, like we can go and read up on it. So where's ZI and pause? Somewhere in here, ZI and pause. It's a hint that indicates the current rate of instruction retirement should be temporarily reduced or paused. The duration of this effect must be bounded and may be 0. Yeah, so you can just do nothing. Yeah, so I'm pretty sure. Yeah. And yeah, they give a bunch of extra examples here. This is also always very nice. I'm taking a lot of my stuff that I talk about, by the way, from these kinds of hints where there's a lot of rationale given. But yeah, as I said here, this is, yeah, hint, blah, blah, blah. This is literally all the spec test. The spec literally has 3 sentences in this extension, and all of this is notes. Those are non-normative. Those are not part of the specification in that sense. Okay, let us continue once more.
Is limited even compared to something like wait for interrupt in ARM, I don't regard it super highly. D tier.
Yeah, this is also why I don't think it's super important. Like there's some other extensions that actually have a like wait for a memory location to be written and stuff like that, or wait for interrupt, I think might be somewhere, which is a lot more useful in many cases.
Let's get back to memory models for a second. As you will have noticed, the previous fences were all about data accesses, loads and stores. But what about instructions, which also need to be read from memory? So far...
Okay, 1 second, I'm going to answer this comment. Yeah, relating to cheat engine, pause and cheat engine. Wait until a certain memory address is changed in the controlled game. Yeah, you would need a different instruction for that, right? There is a different instruction, but like this kind of hardware monitoring needs some extra stuff as well, because mostly those hints where you can say, okay, I want to wait until something changes, are not required to be super precise, because making them super precise is usually a lot of complication in the hardware to like cover a lot of edge cases. And so you usually say, okay, it's like mostly correct, but it's not entirely correct. It's allowed to be incorrect. Like you can have, you also have very similar like C functions, like sleep, for example, that can return before the sleep time has elapsed and stuff like that. They're very similar. Like you're always allowing some imprecision to not make the hardware super complicated. Yeah. So yeah, this, I don't like, pause itself is not helpful. Something else might be helpful. Another question, yeah, is there a good PDF reader that indexes, makes previous text extraction, whatever, to make PDFs work fast, or any system? So that search with Control F is fast, for example. I mean, I am using Ocula, which is with a K, which is the KDE. Okay, search for it real quickly. Which is the KDE one. But I'm pretty sure, yeah, it runs on Windows as well. And they have a mode where they load the entire document into memory, which takes up multiple gigabytes of space, but it will make your thing run extremely fast. Yeah. Yeah. That's the one I'm using. It's been working really nicely. not needed to use another PDF reader.
There is no way of assuring that when we write entirely new code to memory, after a certain point, all instruction fetches will definitely see that new code. Therefore, fence.i.
Oh, the question was how to activate the mode. I guess I can show that. Settings, ocular performance. I hope you can see that. Memory usage, the lowest one. I'm not sure what this is called in English. I have my system set to German, but yeah. So then even like for any ocular user, if you have, as it says here, more than 4 GB of memory, you should already set it to aggressive memory usage. But if you set it to this, it will load the entire thing pretty much, or like the entire decoded whatever thing. And it in like for this specification, I think it uses between 20 and 30 gigabytes of memory, which is fine for me. My system right now has 64 gigabytes, but technically I have taken out 2 sticks of memory for debugging. I have 128 gigabytes of memory in the system normally. So that's that. This is an old server. That's why it has so much memory. So yeah, that's the thing with like memory usage on Ocular. And let's continue. Yeah, so fence I hope you've gathered that, yeah, the point is we don't have any way of preventing the instruction accesses from reading outdated values. This is important because memory loads are different from instruction memory reads, so to speak. Like instruction fetches and memory loads are two distinct things in RISC-V. You can have, for example, memory that is only executable, so you can fetch instructions from there and execute them, but it's not readable. You cannot read the code that lives there. Yeah, so that is the distinction that is being made here. So like the read fence, in a sense, will not actually fence the instruction fetches. It will only fence the explicit memory reads, memory loads.
I exists as an instruction memory fence, which does exactly that. It's a very specific thing, useful for low-level paging code and just-in-time compilers, and it's not super special, but I think it deserves a solid B tier. Conditional instructions are quite common across instruction sets.
Here we go!
And they are very appealing. We can skip a single instruction depending on a condition, avoiding branches and their large overhead. RISC-V once again found the best way of implementing.
Oh yeah, fence in relation to a GPU. Yeah. For GPUs, like if you're talking to the GPU, you also need to do I/O fences in this case to like synchronize the accesses across the PCIe bus and DMA engine and so far properly. Yeah, that's very much a thing you need to do, because like the GPU is even more parallelized to you in comparison to like other processors. Yeah, okay, so here we go, by the way, with the conditional instructions. Finally, to skip like single instructions. As we heard before, ARM has like early versions of ARM had basically every single instructions as a conditional instruction here. But yeah, the GPU fence, like it really depends on what kind of fence you're talking about specifically, but you will definitely need some kind of fence for the accesses to the GPU. Like on the GPU itself, you might need you will need different memory fences. Yeah, okay, let's continue here.
Implementing this by only providing the simplest possible conditional instruction. If condition is equal 0, copy 0 to the destination. Otherwise, copy source register to the destination. That's the behavior of c0.eqz, and c0.nez just flips the condition to not equal 0. Then it's really easy to implement most common conditional operations.
Yeah, so this is like kind of genius, right? You conditionally write 0 to the destination, and otherwise you write the destination. I have it here again. Yeah, so if for EQZ, you write 0 if it's 0. For any Z, you write 0 if it's not 0. And otherwise, you always write the first source register. And
then
yeah.
it's really easy to implement most common conditions.
Yeah, so here you can see some of the stuff that they specify in the instruction listing. I think there might be more, or this might have been all of them, I don't remember. But yeah, you can see like the top ones here, 2 instructions, they don't need a temporary register. Some of those need like the bitwise and conditional select, because and is slightly more complicated. But yeah, you can do all of the basic stuff, conditional ALU instructions with 2 or 3 instructions. And this, of course, you will have pseudo instructions for this in your assembler. Not sure what they're called, but I'm pretty sure they already exist. Yeah. You guessed B tier. I guess you didn't watch the video yet.
Operations.
I kind of assume that people have watched the video before this, because it's sometimes kind of hard to follow through the entire original explanation. I'm giving extra information here.
In 2 instructions and the rest in 3 instructions. I have to be honest, when I started researching these relatively new conditional instructions, I was skeptical, expecting the horrors of x86 and even ARM to creep in. But luckily, this is probably the best combination of elegant...
Yeah, as we saw, like ARM is... old ARM is very interesting with this, and x86 has like condition code prefixes, like it's extra prefixes that make instruction longer, and you can have like up to... How many of them can you have handy? Like 8 or so? I don't remember. Like you can have a lot of condition codes, and that's how you also make the longest x86 instruction. You first chain the maximum number of allowed condition codes, and then you use some really, really large instruction with a lot of prefixes and sub-prefixes, and then you use one with a very, very large immediate. Like, so fucked, yeah. Yeah, also thank you for appreciating the video. x86 doesn't have condition codes. I thought like there is some condition prefix stuff that does something similar to this, I thought. Oh yeah, the locks. Yeah, the lock stuff. Okay, then I was just misremembering it. Yeah, then we are thinking of ARM, of course, with its like the old ARM stuff. Yeah, and rep. Of course, rep stores be my favorite instruction. Anyways, yeah, as I'm saying here, the conditional instructions in RISC-V, branchless programming, perfect. As we said before, branchless programming, extremely good.
And powerful they could have found as a solution to this problem. A tier. Okay, so the future extensions are going to get very complicated. There are going to be a lot of configurations we'll have to choose, errors being reported, and hardware information we'll want to read.
Yeah, the reason the conditional instructions are not in S tier is because this general idea is not super, like the general idea of branchless programming is not super new or innovative. And also it's not like not the most powerful, and like I still... It's also not like in the it's not in the core instruction set, right? It's a bit... I don't think it really deserves it. Like S tier are just the instructions that like kind of hold the entire instruction set together, I feel like. That's the reason why stuff is in S tier usually.
This is what control and status registers, CSRs, are for.
I've very well avoided talking about CSRs so far. Which is hard if you talk about more advanced hardware stuff. It's always like, oh, this CSR does that, and so on and so forth. Like thousands of pages of not thousands, but hundreds of pages of register descriptions for CSRs exist, and stuff like that.
There are 6 basic instructions for interacting with them directly. All CSR instructions are atomic read, modify, write, which is important as some of them are shared between cores. The read-write instructions write...
Yeah, I'm not even, like, for some of them, to me, it's kind of unclear which ones are properly shared. And sometimes it's also like you can decide how you want to do it. For example, MISA is kind of one you can share if you make it read-only. because like if you have multiple cores that all implement the same ISA, then yeah, that's fine. Oh yeah, I love CSRs too. CSRs is like the design here is really cool. I mean, like initially when I first was reading about RISC-V and first also implementing CSRs, right? In my software implementation, I implemented CSRs. I had to write like a separate module for this. I was thinking, it's kind of annoying. They could have put it like in a special memory mapped IO region or whatever to like make it more orthogonal, to have not a special IO space. But I actually think this is much better. For one thing, like most of them are like, very specific internal processor stuff. You have some external stuff, but it's very basic. And like by keeping it out of the memory space, this is the cool thing. Like the memory space is entirely up to the specific platform and to the implementation. You can do whatever the fuck you want with the memory space. So there's like a lot of flexibility where you can position stuff. And the CSR space is, of course, very strongly defined. CSR addresses, I don't think I ever mentioned this. I think they're 12 bits. So they're like, there can be up to a few thousand CSRs in theory. Like not all of them, like some of them are aliased by definition. Some of them are like read-only variants of the other ones. There's some stuff in the standard for that, but there are at least several hundred CSRs, and not a lot of them are occupied right now. And like I think some of the CSRs in general are maybe a bit unnecessary, but like the most of them, like some specific ones are necessary, but in general, this is a really nice design. You can probably also like put CSRs in certain functional units where you specifically need them. As I said, you can have shared ones or ones that are specific to a processor. A lot of the CSRs also provide different views on the same like functional bits. So the actual state that CSRs contain is not very large. And so yeah, there's a lot of cool things here. And of course, like this read write and also the set bits and clear bits that we're going to hear about in a moment is very convenient. So you can do really fast operations on the CSRs. And yeah. And yeah, laughs in x86, in byte, out byte. Yeah, exactly. Like the problem is really that, or the thing is, CSRs are like especially never for I/O. The most that CSRs go outside of the physical memory protection things in some CSRs. Like you can use CSRs usually on simple systems, and from machine mode software, so from the firmware. You can specify certain memory regions as read only, for example. And this is like, I think this is mostly for low-level firmware stuff, for like microcontrollers, whatever. Like this is the most that it goes outside of the core and needs to talk to the MMU. And I guess if you read and write those CSRs, you have some kind of special case for talking to the MMU. But in general, this is like internal stuff. As we'll see later on, there's like flags for the vector instructions. There is stuff for the floating point instructions. There are the ISA, the extensions that are enabled or disabled or just in general available. There's like exception information when you have a trap, when you have an illegal exit, when you have a page fault, an illegal instruction. Like the processor will write stuff into a CSR so that the kernel can handle a page fault or an illegal instruction, for example. Yeah, this is all like very, very internal stuff. So yeah. Which ones are for I/O? Like in general, I/O is memory mapped. So you access I/O through memory. This is the case with almost every modern system. x86 has an I/O space because it's absolute fucking dogshit garbage, obviously. Every explanation in x86 can be explained with that, every design decision. Or there are no design decisions in x86. There's just random throwing things at a wall. This is facetious, of course, but I'm just saying, like, you don't need the I/O space in x86. You could have just gone with memory mapped I/O from the start, and it would have been just fine. Yeah, like, yeah, sure. x86 also has MSRs, which are like CSRs, and ARM also has these hardware registers. So this is not a new concept, but in general, the implementation on RISC-V is very, very solid. So I still like it. Yeah, the PCI I/O space, like talking to PCIe devices like graphics cards, for example. This is or talking to USB host controller interface, whatever. These are all memory mapped, even though it's I/O space. And this is also why RISC-V has a difference between I/O memory space and actual memory space. That's what we saw earlier with the fences, which can do I/O fences or read-write fences, which are for normal main memory. So yeah, but it's also something a bit unique, I think. But yeah,
the source into the CSR and read the old CSR value into the destination. The set instructions set the bit from the source, while the clear instructions clear those bits. Both of those are more useful than they sound, since many CSRs contain multiple bit flags, and we usually...
Yeah, I just used M status for the example here. I don't actually know what half of those mean. I think it's like these basically enable the IE is always interrupt enable, like they enable interrupts on certain execution levels. They changed the oh god, I forgot what VS is. MPP I think changes the current privilege level. So what are you running in user mode, or are you running in kernel mode or in firmware mode? Like the privilege level, if you know about rings in x86, right? Which ring are you running in? This kind of stuff. There's MXR sounds familiar. I don't know, but yeah, there's MPR. You can. Oh yeah, I think there's one of them specifies if you. I think SUM is for if you can read and write user memory from supervisor mode through virtual memory, so you can avoid just reading random application data from the kernel, which is a kind of a security feature. So there's like a ton of stuff in M status, and like this register has it all. VS is the vector status. Thank you. Yeah. So it is actually vector related. I was thinking maybe it's vector related. I don't know. Anyways, this thing has a bunch of unrelated stuff, and you want to just be able to set and clear single bits. That's why the set and clear instructions exist. And also there's a bunch of pseudo instructions for not actually doing a read or a write, because that's also something I don't talk about. If you use the 0 register with most of these, you won't actually either not do a write or not actually do a read. So it gives you the, like, there are some bits or many bits in many CSRs that have an effect if they're written to, even if you don't write anything, even if you don't change the value. So you actually need this, and you need special behavior around the 0 register to not affect them, so to speak, to not, like, for example, cause pipelining problems or cause some kind of spurious interrupt or whatever. So there are some special cases here. I didn't go over them in detail. Like, this is getting heavily into like low-level firmware stuff and kernel level things and paging and so on and so forth. Yeah. A 0 register is pretty much like /def/0. If you write into it, the values get discarded, and if you read from it, you read 0. But in this case also, I think if you write the 0 register value into a CSR, nothing gets written, instead of entirely zeros being written. So this is an important distinction. And also, by the way, the CSRs, I don't talk about this as well, CSRs are always the same size as your integer registers. So on RV32, there are 32 bits. On RV64, there are 64 bits. That's why you need a few registers are split on RV32, because they're too large to fit in 32 bits, and they're like one single register in RV64, which gives you some nice symmetry, and like you have special mappings for those. It's overall an extremely well-designed system. If you want to read about it in more detail, go read the specification. It's freely available. I linked it in the description, right? It's also easy to navigate and go to the parts that you actually care about, and they always give very nice explanations of everything and rationale and so on. So I think I should have done that more. The RISC-V specification is a really, really excellent and nice spec to read in terms of hardware specs.
Actually only need to change one or a few of them.
No, there's not a null register and a random register. You don't really need those. I mean, there are CSRs or there are extensions that give you randomness. And I mean, the 0 register is also a null register, right? Because anything you write into it will be discarded, like you pipe stuff to def null. Anyways.
Also the immediate instruction versions, which are useful too, since most data lives in the lowest 12 bits of any
Yeah,
given
this is also, I thought that they had the same immediate as any other as any other like immediate instruction, like the arithmetic ones, for example. But no, the immediate is actually smaller because you need the CSR address, which is already taking up a lot of space. So you need you only get 5 bits there. But this is actually like a lot of CSRs are designed around this. They're designed to have the important shit in the lowest 5 bits. And the ones that are larger usually have different CSRs that provide different views on the same bits. So you can use a different CSR address to access the same stuff in the lowest 5 bits and use an immediate instruction. Again, great design.
CSR register. Overall, given how well designed the CSR system is and how many different important functions it performs across the system, I have to give these instructions a solid A tier.
I guess thinking about it now, I might have given them, should have even given them S tier. But I guess I'm not really a person for like all the firmware stuff, so I don't know. They deserve S tier. If they're in your tier list, if they're in S tier, I think you're not doing nothing wrong. I guess what this all teaches me is that in machine instructions, you don't worry about 8-bit alignment for some reason. And no, this is specific to CSRs where you have like specific bit flags. So you want to pack as much stuff as possible in as few registers as possible, usually. At least if this data is related. So that's why you want to do this kind of stuff. And this is actually true for a lot of hardware registers. Like if you're, for example, like microcontroller registers, like anything where you're talking also about external hardware registers, they often have these kinds of bit flags because you want to just pack stuff as much as possible. Yeah, this is something pretty common in like low level software and like firmware related stuff, like anything embedded.
I'm going to give you two.
Oh yeah, secret. Sorry.
A solid A tier.
Secret, a third thing, of course, is that's the joke. Like M is the secret third gender or something, I guess. I didn't want to tell you what this extension is about before actually doing the skit here.
I'm going to give you 2 seconds to think about this. Which fundamental arithmetic operations are missing from the base integer instruction set?
Like, yeah, it's called literally M, but what it is for? What is it for?
Pretty obvious, hopefully. Integer multiply and divide.
Yeah, multiply and divide, of course. But yeah, that's very interesting that we're like 29 minutes in and we're only now getting to some of the most basic arithmetic that you can do, as you'll see.
There is an equally obvious reason why those are not in the base instruction set. Implementing multiplication and division in hardware is extremely expensive, so it's part of a separate extension.
Yeah, so the thing is, multiplies themselves are kind of okay. You can do like a tree-like multiply. You should, if you have never heard about this, like hardware multiply and divide, you should look this up. It's kind of very interesting. Like the problem, like multiply is kind of okay. You can do like a tree-wise combine of more and more bits. But divide basically either requires you to do multi-cycle divide, where you shift stuff around. But you can also do that for multiply, but multiply is also easily possible in one step. And if you want to do it in one cycle, it's actually super expensive. Like on the softcore I wrote, like we implemented multiply. We are lucky because the FPGA we used has a DSP, which has a hardware multiplier inside. So it just used like 2 or 3 of those DSP chips for the DSP blocks for those multiplications. And yeah, the M mul, yeah, M without division, exactly. That's what we should have implemented actually in the or that's what we did implement in the soft core, but the extension didn't exist back then, so we couldn't actually tell the compiler about it. So just in our handwritten assembly, we had some multiplication and whatever. Yeah, floating point divide is a lot faster. Yeah, and yeah, division is really hard. You usually have to do it multi-step, like in some like. At least in some architectures, like division can be slower than a level 1 cache miss and stuff like that. It's super slow. Like on our FPGA, division would have taken 130% of the available blocks. So everything else was like 50% of the available blocks with our 2 cores and our SOC and our memory, everything 50%. One 64-bit divider, 130%. Just to give you an idea. I mean, I'm pretty sure this is very FPGA specific. We're talking about the Spartan 7 from Xilinx, in case you want to look it up. But yeah, it is fucky. And yeah, a use case in the while that do division in bulk. Not sure, but yeah, multiplication is in general also more important than division. So yeah. Also, sorry, did my stream just drop out? Oh no, okay, it didn't. Saw some loading here, but no, stream was fine. Okay. Yeah, anything doing a lot of math may do division. Like, yeah, true, but in general, multiplication, of course, is a lot more useful. That's why we're later going to see fused multiply add for a floating point. And yeah, you can do some cheats with division. Like often compilers will implement divisions by not doing a divide, which is usually faster, same for modulus, but yeah. Let's continue with the video.
These are the basic multiplication instructions, so you'd expect me not to have...
Okay, 1 second. I will have to be away for a moment. I appreciate the wait. We're back and better than ever. So yeah, let's continue.
Much to say, but that's not the case. After all, a 64 by 64-bit multiplication can yield a result up to 100. All the high instructions come in, which give us the upper high.
Of course, the same thing for 32 by 32-bit gives you 64-bit. And actually, like just the past few days, I've been implementing some like very interesting floating point format, DEC64, in case you know about it. And I actually need to do like, or it makes it easier for the implementation to implement like some of the multiplications by doing a full 64 by 64 equals 128-bit multiplication, and then shifting the result down and like looking at the overflow there, which is quite trivial in RISC-V. You can just do the high multiplication, then you have the 2 parts of the results immediately.
Half of the result. They come in 3 variants for doing a signed-signed, signed-unsigned, or unsigned-unsigned multiplication. In case you're wondering, math tells us that for the lower half of the result, signed or unsigned does not matter, so we don't need these variants here.
Yeah, I was thinking about putting an example in there, but it would have been, we would have gotten into like, how does multiplication in binary work specifically in 2's complement and that kind of shit probably. I don't actually know myself why it's not a problem. I just trust that this is true, and yeah, we don't need it for the lower half. So yeah.
2 instructions for 1 multiplication sounds kind of expensive, but if we put these instructions right next to each other, it It's pretty easy for a
Yeah, never do math on stream, definitely not. And yeah, we can see here more macro op fusion, yay. So this only performs one multiplication in most decently optimized processors.
advanced processors to only do the multiplication once and use the result twice. Overall, super well designed and useful, A tier. Division and remainder are a bit simpler, as their results always fit in one register and the only variant necessary is an unsigned variant. Once again, subsequent division and remainder instructions can be fused to only perform the division once. However, it's quite interesting.
Yeah, and as was noted before, there is a separate like small instruction, small extension now that only contains the multiply instructions and not the division and remainder ones. So for FPGAs, for example, or for really, really small stuff that can't do the division efficiently. So there's like even more splits in here inside of the M instruction set. But like in general, you're going to have M, which is going to have both of them.
Interesting what happens if we do the infamous divide by 0. Many architectures raise an exception here. RISC-V does not and produces well-defined values that match the most common hardware implementation behaviors.
What about POW with module for cryptography like RSA? There is a cryptography extension and there's also a vector cryptography extension. And the way that it's looking right now is probably going to be for desktop processors that they are not going to have the cryptography extension, so ZK whatever, but instead going to have the vector cryptography stuff because vector is mandated anyways. And like a lot of the stuff like AES and RSA benefits from vector registers anyways. So yeah, they have some stuff like modular power, fast exponentiation, Galois field multiplication, so on and so forth. This all exists, but it's like kind of out of the scope of basic multiply and divide.
What a genius move! And not causing hard.
And also this is super cool. I don't quite know how this looks like in hardware, but they say in the spec that this is what it usually looks like in most hardware implementations. When you have division by 0, you just get these kinds of results, and or an overflow, of course. Will it support Kyber? Yes, it will support Kyber because you just need a bunch of conventional instructions for that. Like, depending on what exactly you need to accelerate. Like, whenever we're looking at cryptography, we're looking at specific instructions that we want to accelerate. And also the problem is some cryptography is better designed for hardware and some is better defined for software. So AES is better designed for hardware and Cha-Cha-20 is better designed for Poly 104 and Cha-Cha-20 are more defined for software. Like there's a lot of things here with like NIST, like the United States standards body always prefers hardware first stuff, so stuff that is faster in hardware, when in general a lot of stuff will just have to run on software, and so it's better to actually prioritize stuff that is efficient in software. That's why many people rather prefer Cha-Cha-20, Poly 104 and things related to that instead of AES. Same thing for ED25519 is, I think actually ED25519 and RSA doesn't really make a difference. Both of them are probably equally fast in software and hardware. But of course, we do a lot more symmetric crypto than we do asymmetric crypto. So having the symmetric crypto really fast is more important. And I don't actually know how Kyber specifically works. I only know like the basic Veritasium explanation of linear grids and shit. But I'm pretty sure it's a similar thing, right? You don't need it to be extremely fast because you're only doing it once for key exchange, ideally. That's the whole point. Asymmetric crypto is the fast stuff you do all the time, and symmetric crypto is the stuff you do once to get the very high security level and the very high requirements, and then you use it to derive a key through a Diffie-Hellman exchange, and then you run symmetric crypto through the common key that both sides have derived. And this is not going to change with post-quantum crypto. Veritasium did a video, I think, more in general about like lattice, like the lattice linear algebra stuff that Kyber uses, and like in general about the post-quantum problems and or the quantum problems. Like, I'm not sure, it's not specifically about Kyber. It's a quite old one. I think it's over a year old. Anyways, we got sidetracked talking about cryptography now, which I guess I know too many things about. But I still don't feel qualified. Like, I very much have imposter syndrome when it comes to cryptography, even though I'm quite knowledgeable about it, I feel like. But like, the more I know about cryptography, the less I understand, and the less confident I feel like I know anything reasonable about cryptography. Anyways, let's continue here.
Hardware exceptions makes things infinitely less complex.
And of course, yeah, this is a great design decision. Just no hardware exceptions in basic integer operations. Just less hardware exceptions, please. Less hardware exceptions. If the software cares about division by 0, it can check it manually with an SLTI or SLTIU, or SLTIU specifically, yeah. And it's like, yeah, much better.
Here. Once again, when we're on 64-bit, we need some way of doing 32-bit arithmetic, so these instructions exist to help us. Same story as before, C tier for necessary but boring features. Did you think that memory models would not come back to haunt us again? Funny. Let's talk about...
I think I used that track before when in relation to the memory models, but I don't remember.
Atomic operations, operations suited to multiprocessor synchronization. So sometimes we have...
Yeah, here we go. Possibly my favorite part of the video, LRSC.
Simple atomic operations, just the read, modify, write without being interrupted. However, those are really not suited for more complex operations where we need more than just a single atomic to ensure processes are synchronized. There are many different solutions for this problem, and RISC-V chose one that I think is somewhat unique while still turning out incredibly useful: the load reserved and store conditional pair.
So actually, after the video, again in the porting software guide, I guess I'm going to show this to you. Software porting, where are we? I found out that LRSC is actually not a new thing. It's quite old. It has existed in a few RISC instructions. I think it even exists in ARM, at least to some capacity. 1 second. Also, by the way, in case you're wondering, over here is the cryptography extensions. And down here is the vector cryptography extensions. Where's the porting guide? Code porting and mapping guides. Here we go. Yeah, this is yeah, power. Power has load and load. Has load reserve and store conditional. ARM has load exclusive and store exclusive, which are actually the exact same thing, apparently, according to this mapping. And also, yeah, some Linux. Yeah, I think this is where I got the acquire and release stuff from. This is the more precise way of doing acquire and release, or like, yeah, so some of these, I guess. But yeah, this is so ARM has load reserve store conditional. Power has load reserve store conditional. So this is actually quite an old idea. ARM actually only has load reserve store conditional. Don't have AMO like operations, so no atomic add. Yeah, that makes sense. I guess it's kind of nice that they exist in RISC-V. I also didn't think, like, immediately the first time I read spec, I also didn't think they were particularly necessary. They didn't feel particularly necessary to me, but I guess they're useful in some situations. And I mean, people are also trying to put like a full double word compare and swap into RISC-V. Like, there is an extension for it, and it's optional and might be mandated in the future. I don't know, because they want to have faster CAS, I guess. Like, fuck all. We need 4 instruction for CAS right now. It doesn't fucking matter. It doesn't fucking matter. Anyways, I will talk about this in a second anyways.
First, we execute a load reserved, which is a normal memory load, but also makes a reservation on the address we just loaded from. Then, sometime later on, we can execute a store conditional, which seems like a normal memory store, but is actually special. If the store conditional is to the same address as the last load reserve, and no other processor has written to that address in the meantime, it succeeds and performs the store and writes 0 to the destination register. Otherwise, it fails and does not store to memory and writes non-zero to the destination register. This means...
Okay, I'm getting some comments here. First of all, ARM has atomic adds and casts in the large system extensions. Yeah, of course. Yeah, okay, acquire and release semantics are just for acquiring and releasing locks, basically. For acquire semantics, you want everything that happens after the acquire, everything that is in the instructions after the acquire, you want to definitely happen after the acquire. And same with release, you want any instructions that are before the release to definitely happen before the release. If you think about a lock, you want everything like between the acquire and release is the place where you can execute the code that you want to execute while you hold the lock. So you need to make sure that they're actually in between there, because as we talked about before with memory models, normally there can be random ordering, so you have to limit the ordering in that case. You'll have to do some more reading on your own. I don't really have time to go into the details, but this is the rough idea of acquire and release semantics. Yeah, so here, by the way, the reservation set valid thing, this is very imprecise. First of all, we can have spurious fails. So spuriously, the processor can just decide that the reservation set is no longer valid. And this can just happen randomly. This is one of the things I said earlier, right? You don't want to require things to always be correct and always succeed, because that will make the hardware unnecessarily complex. You want to allow some spurious failures and some spurious deviations in these kinds of synchronization situations. You definitely want to do that in general. I mean, acquire and release are like locking are necessary for a mutex. Yes, a mutex is a kind of lock, but in this case we're talking about lower level primitives, lower than the mutex. Mutex is a very high level primitive. Anyways, so this is the first part, the first limitation here. And second of all, the reservation set can be larger than the address. So if there's a write to an address next to the LR, next to the address we loaded, it might still invalidate the reservation set and fail the store conditional later on. So the reservation set, for example, usually is tracked on a cache line size, so like on 64-byte level and not on like a 4-byte or 8-byte level. So this is like the main things that I kind of am simplifying here. And then I say here, with any complex operation, that's not true. That's also in the thing here. They are limited to the so-called, where is that? Here. Where here, yeah. They are limited to the so-called constrained LRSC loops. Let's look at LRSC loops, wherever the fuck that is. A, please. A, here we go. A, and where do we have? Yeah, eventual success. So basically, here are the conditions for what are constrained LRSC loops, and these are the only loops that the hardware has to guarantee will eventually succeed, and they don't have to fail all the time. And there are some very specific conditions here that are relatively easy. You can read them on your own time if you want to. But the main important thing is that it can be at most 16 instructions. So there is some complicated hardware tracking here that has to track are we in an LRSC loop, and then has to like somehow guarantee that it will eventually succeed if there is a condition in the hardware that can allow it to fail all the time without any fault of the programmer. So this is like, yeah, a thing. Say like, yeah, this is like cache stuff, blah, blah, blah. But like the point is really that this will succeed eventually. There's some very specific spec language around how this exactly works. We're getting back into memory models, kind of. We don't have to look at this too precisely, but really the point here is that like not all complex sequences of like that contain LRSC have to succeed. but the ones that contain at most 16 instructions and fulfill and don't have any branches and some other conditions, they have to succeed eventually. Basically, that's the gist of it. Yeah, again, this is multiprocessor synchronization stuff. It's complicated. Don't worry if you don't understand all of it. I don't understand all of it either. It's just I'm trying to give a gist in the video here, and now I'm explaining some of the more nuanced parts of it. And like all of the detailed nuances are mostly important for hardware designers and people that actually want to write LRSC code themselves, which is pretty hardcore.
That we can do a read, modify, write with any complex operation we want.
Yeah, right, so this is not quite true.
And we can check if anyone else modified the memory location in question while the operation was still ongoing. In that case, of course, we have to retry the operation. I hope it's obvious how many synchronization problems we can solve very well with these instructions. The standard example is the all-important compare and swap operation, which takes...
Yeah, so this is basically CAS as it is given in the specification, except the specification also contains a code to return from the function. But I didn't include that because I think CAS will almost always be inlined because it's just 4 instructions. So you load the value, like the from the pointer. If it is not what you expected, that's a compare part of compare and swap. Then you fail, of course. If it is equal, then you fall through here. You try to write the new value A2 to it. If that didn't work, then someone else wrote to it in like during this time, which is like very short window, but fine, and then jumps up here. And this is a constrained LRSC loop because there is like only a branch like out of it, so there's no branch internally, and this is less than 16 instructions. It's only 3 instructions here, so that works. And yeah, if we don't branch up here, of course, then the store conditional succeeded and wrote 0 to T0. That's also a thing, like store conditional writes whether it succeeded or not, so we can check that very easily, and then we can continue with the success code. Anyways, yeah.
Only 4 instructions in line. But there are many other applications for this brilliant instruction pair, S tier. In most cases though, LRSC and manual read, modify, write is way too complicated. We just want all of it to be done in one instruction with guaranteed success. This is what the other atomic memory operation instructions are for. They just do some calculation with the memory value and the second operand, store the result back in memory, and return the old value in the destination, all in one go. For example, with AMO add, we can do a very easy parallel sum reduction.
Yeah, I wrote a very primitive thing here, which adds up like 2 values from an array into some place in memory. Oh my god, I'm getting tired. I should get done with this relatively quickly. Yeah, so this is one example, but usually you won't have stuff like this because this also runs up a lot of cache flushes. Like AMO operations are usually incur a cache flush penalty, so you don't really want to do that, do it all that much. But yeah, you like AMO, swap, and XOR maybe some of these are a little bit more useful. I can't really think of any case where you actually need them, but there's probably cases where you need them.
Atomically in memory. Overall, while these instructions are not mind-blowing like LRSC, they are still quite useful. B tier. These 4 work the same way as the other AMO instructions, but I find them to be quite a bit more interesting since they do maximum and minimum operations, which seems to me more useful in some cases and more unique.
Yeah, this is just a gut feeling thing. I feel like there's cases where you want to track some kind of minimum or maximum, like of some statistic of a parallel operation maybe, and you want to write that atomically right, and you don't do that many writes. You just occasionally write it out, and you can keep track of this maximum or minimum in memory independently, and just not worry about anything.
Unique than the others. That's why I'm bumping them up to A tier. Okay.
Here we go with a floating point. I mean, there's also why this is kind of short, because like fundamentally most of this is just IEEE 754 floating point. We all know how IEEE 754 floating point works. Most of this is just implementing all the required stuff from the spec in hardware. Not all of it, but like as much as possible in a somewhat performant way.
This was a long time coming. Floating point. The instruction count is going to almost double because there are just so many operations with floats. I'll be breaking with my previous rule and group these instructions a bit more sensibly.
Yeah, I did this because like if we look at the we look at the G listing again, where's that? Somewhere down here. Like here we go with RV60 32 64 multiply atomics. Yeah, also by the way, I didn't mention that there's like double word and single word variants of all the atomic stuff, which is one of the things I said I would always leave out. Yeah, and then we go to float, and like things are just ordered really randomly. We have like convert, then we have equals, and we have another convert, then we have the move here and a move here. And yeah, and I mean, I do go through this somewhat in order, you will see. Yeah, and then we also have like the 64, like if you have 32 or 64-bit single position float with 32 or 64-bit integers, that also changes stuff because you can also have extra conversions. So this just messes up things. Here you have 64-bit floats but 32-bit integers. That's actually something you can do in RISC-V. I am 100% uncertain why you would want to, but you can. And yeah, so this again like adds stuff in random order, and then we have the D as well, and yeah, I think that's it. And then we also have the quad word one for 128-bit floating point, which I don't discuss, and also the half floating point, so 16-bit floating point, which both of them I don't discuss. They don't add really anything new. I don't know why this exists over here. This is, by the way, the wait on reservation set. This is the wait for memory reads or writes. And here we have the CSRs that exist in G. So these are the float ones. They are the first few addresses. Anyways, let's get back to the video.
Since a lot of them do almost the same thing but are still listed in completely different parts of the table. And I'm covering both single and double precision floating point at the same time. Starting simple, we have memory loads and stores for floating point values. This is really nothing special. As you'll see, the float instructions are just like the integer instructions with their load store architecture. C tier for being a basic bitch.
Yeah, but this, guess I could have put this in B tier, but I mean, it's just the load and store. What do you want from me? At least there are floating point loads and stores. I think some architectures don't have that, but not common ones. Common ones all have that.
Basic floating point operations are as you would expect.
Is there something to disable IEEE 754 subnormals for audio software to work faster? No, I am not aware of anything. And this is also like, this is the thing, like this is not required for the standard, right? So this would be an extra thing that wouldn't be standards compliant. So no. And also, by the way, this like very slow, I think I know which video you've seen for like slow subnormals. This is not really a thing on modern hardware anymore. It doesn't really matter on modern hardware. But there's a is there a DNZ? 1 second. F flags, there is FCSR. Let me actually, I guess you can have a look as well. Let me actually look at F again. Floating point control. Now we just have rounding mode. Rounding mode. I mean, yeah, we have. I don't think the round towards 0 does that. I don't think. I mean, you have an inexact. Wait, no. What is it? Not sure. One of those flag signals are denormal, possibly. I'm not sure. But yeah. Yeah. So normally it's detected properly. I guess it's underflow and stuff like that. Okay, did the video actually show a proof of concept that it actually is affecting audio software? Like, I guess it is. Yeah. I mean, in general, right, my opinion on IEEE 754 floating point is that it should go die in a fire. That's just the thing, right? I absolutely hate IEEE 754 floating point. There are a few good ideas in it, and most of it is ass garbage. Especially like the most of the stuff related to NaN and infinity behavior is kind of shit. Like you need NaNs, or NaNs are used for concept, but I would have implemented them differently. And I think in general, decimal floating point is more important, especially because you can then do money in floating point without risking anything, which is super useful. And also the requirement of having everything normalized is like, it increases the range of your stuff, but it makes everything slower because you have to normalize all the numbers all the time after the operation. At least in simple operations, or at least when you're converting, you have to normalize all the time. IEEE 754 is F tier, but not like the float instructions themselves get different tiers because like they are just judged for how much in the RISC-V spirit do they implement IEEE 754 floating point. Like we don't, at this point, obviously, I know we don't really have a choice. We have to implement floating point. Like everyone's dependent on it, right? There's no way around it. There is a few alternative formats that are used in like AI and stuff, like BrainFloat 16, for example. But in general, no. The good alternative is DEC64, or some redesigned binary floating point format that doesn't have all of the garbage and all of the bad legacy decisions that have been carried in the standard since the 80s when it was created. Like this is an old standard, right? We're still using a floating point standard that is effectively from like second generation supercomputers. It's kind of ridiculous. And DZ, is there no? Yeah, no. The DZ is the divide by zero flag. So no, this is not. I don't think you can disable subnormals in the basic floating point extension. Maybe in that case we should make a suggestion to extend the CSR, the what is it? FCSR by another bit that lets you specify disable subnormal arithmetic. Like that sounds like a reasonable extension to have if you want to implement DSPs in RISC-V, and you want to, like, they might have hard coded that to 1 or whatever. Then that sounds reasonable. No, DEC64. DEC64. DEC64 is great. Is great actually, and you're not going to convince me otherwise. No, in general, like also there's no real performance difference in floating point between architectures. Not that much. Like the basic floating point operations, like addition, multiplication, subtraction, so on and so forth, you can reuse the same hardware everywhere. It's just IEEE 754. It's implemented all the same. Just basically your front end is the same. Yes, RISC-V is good, but also RISC-V doesn't really have an option. RISC-V can't just, it is a blank slate implementation, but it's still trying to be realistic and useful. And that's kind of the point. It's not just a research architecture. It's also a practical architecture. So it needs to have IEEE 754. And it also has a bunch of other formats, like the half, float, and there's a bunch of other stuff. I think there's even a brain float extension. So if you want to like implement your AI stuff in RISC-V, you can use that, I guess. Anyways, let us continue.
Them, and they're very similar to integer operations in all regards. There are no exceptions when we divide
same
by
thing as
zero
before.
or otherwise produce an NaN. There is just a flag set in the floating point exception CSR.
Yeah, we just saw this, right? You have a bunch of flags here for NV when you produce a NaN, divide by zero, overflow, underflow, and inexact. I'm not actually sure what inexact means and underflow means, but yeah, these are just standard things. If you want to know that, like you can read about IEEE 754 in general if you want to know about these in more detail. It doesn't support DEC64. We could, because RISC-V is so extensible, we could write a hardware extension. We could write an extension for DEC64, which would be great. I would absolutely love it. Like this is the cool part about RISC-V, right? You could just do stuff like that, and nobody's gonna stop you, and it's very much in the spirit of things. Yeah, let's see. Yeah, let's see. I don't even remember.
Is that the rounding mode can be set directly in almost every instruction, and we can also set it in a CSR as a dynamic rounding mode. Some of these rounding modes are not even supported by x86.
Yeah, I think Handia Dion, you might want to correct me, but I think round to zero is not supported in x86. Like one of these, at least one of these, is not supported in x86. I don't remember which one, but I remember when I implemented the rounding mode stuff for Serenity, I didn't need to implement, or I added like an extension on top of what C provides, because C doesn't have all of these by default, right? C has only 4 of them. I think round to zero is the one that's missing. I think, yeah, round to nearest, default, of course, round down, round up. And, oh no, I think it was, oh yeah, so it was away from zero. So round max magnitude, so ties to infinity. So yeah, so this is the one that's not in C, that's not in x86, and they just implemented it, which is really cool. Because it is sometimes useful. I guess it's literally the opposite of round to zero. So in my opinion, it actually makes sense if it exists. To zero is not fair rounding. It possibly means truncate. Yeah, I don't know, but this is like if you look at the IEEE standard, it will tell you what this exactly means, right? So this is standard stuff, but the C standard doesn't require a round max magnitude, so x86 doesn't have it. And it might not be implemented in x86 either, it might be in the standard of the IEEE standard, and on x86 you just have to emulate it. I have actually no idea. Like there's a lot of weird features of the IEEE standard that people don't generally use, so it's not well supported in hardware. It's just really slow to use. Yeah, away from zero is, yeah, it's okay, so it's a default C99 route. I just mean like it's setting the rounding mode manually in C, stuff like that, which is not even possible by default unless you enable it through a compiler flag. Otherwise, the compiler will just optimize your rounding mode setting away. Yeah. Arithmetic should always use to even as that average out. Yeah, of course, like in general, you want to do a round to nearest, which is ties to even, I think. So this is like a thing for very, very specific code that where the compiler can know, okay, if I use this specific sequence, I get the desired result and whatever. This is why you can specify them statically or dynamically. And in general, like what they also say in the standard is probably if you change the rounding mode, you will flush the pipeline. So that's that. It's probably bad for performance.
Definite A tier for the design here. Now we come to a very controversial part of the instruction set.
I mean, I say it's controversial, but honestly, I can't find these arguments anymore. I would just think that this seems kind of controversial, and like I think it's not the absolute best use of space.
Fused multiply add. The problem with these instructions is not that fused multiply add is not useful. It is in fact very useful for lots of math, especially linear algebra. The problem is more that these instructions need 3 source operands, which takes up a massive amount of instruction encoding space. I have seen...
Yeah, you can see here, we have the opcode here, which is, yeah, one of these 4. We have destination register, we have the rounding mode, which is the stuff I showed before. It's actually, yeah, they need 3 bits because they don't just have 4 rounding modes. Then 2 source operands, 2 source registers in normal position, then format for single precision, half precision, double precision, quad precision. So that's also very normal. And then the 3rd source operand. So they're using like all of this space to the maximum extent. This is pretty hardcore. So that's why you need a separate major opcode. These are called major opcodes over here. In the separate major opcode for every single one, from multiply add, multiply sub, negate multiply add, and negate multiply sub.
Quite a bit of arguing that this is very much not worth it, but these instructions should have rather been used for vector instructions with dedicated masks and the like.
That's also my argument, by the way.
When reading assembly code, it is notable how much these instructions are indeed used in practice.
Yeah, when I had a weird thing when I recompiled the Serenity libc, or sorry, when I looked at my old compiled Serenity libc, these fused multiply adds were gone. LLVM had just inserted like an add and a multiply and then an add and a multiply and then an add, instead of like using the instruction for the fused multiply add, right? It was super weird. Yeah, it just and like when this is the code that I have. This is some of the test code that I have for my instruction decoding, and this is like an older implementation of the hyperbolic arc sign, so the trigonometric math function, right? But yeah, in general, like if you look at math code that is compiled with the proper flags, and it seems like at least on Godbolt this is fixed, so in current upstream LLVM this is fixed, like it uses fused multiply add all the time. Like I am not sure what the compilers are smoking, but they really love fused multiply adds. So like this is why I don't have a strong argument against it, because it is clearly something that you can actually make a lot of use of. And like fused multiply add units, so like multiply accumulators basically, like this is pretty standard components. You have that in FPGAs even. Like it's pretty easy to like do a multiplication and an add at the same time in hardware, and also this gives you more precision, right? So there is a lot of advantages to having this. Yeah.
For basically everything in floating point math, so they seem to be really worth it. I'm still giving them B tier overall.
Yeah, this is why I placed them kind of highly. If they didn't use up that much space, I would have put them in A tier.
Yes, we only...
I don't know how, to this day, I don't know how sine and cosine work. Should look up your code. Well, how they work internally is really complicated, and it depends on your implementation. There's a lot of different ones. The most basic ones do Taylor approximations. You can also do lookup tables. There's a lot of ways of implementing it. But yeah, depends. And of course, sometimes you have hardware instructions for it, which is my argument here. We should have had hardware sine and cosine, but we only got square root.
Only have a single advanced math function as an instruction, the square root. Not sure why exactly. There is a lot of space for others. It's
like if we go to the over here, once again scrolling to the end of the fucking file, RV32F. No, where were we? Yeah, so basically they have like, I mean, they don't have like, they're of course sharing this instruction coding space with a lot of other instructions. But for example, they have this unique pattern, right? And they could use this one for basically 32 different single operand instructions here, and 32 would definitely cover everything. You could do sine, cosine, hyperbolic, tangent, the arc variants of it. You can do inverse square root with the higher precision. Remember Quake and stuff like that. Hardware sine cos are quite slow on x86. I guess so. But then the question is, RISC-V is designed for fast trap and emulate. So then you could emulate this in like a fast firmware routine or in a fast kernel routine or something like that. This is really also some of the design stuff behind RISC-V, that your traps are really fast. Our context switches, traps are not slow, they're really fast. They're supposed to be fast to be able to emulate instructions that don't actually exist in the hardware. I wouldn't recommend looking at Serenity code. Most of our math functions are not very well implemented, and this is true, absolutely. I wasn't recommending it anyways. So yeah. Anyways, I agree, Handy. This can be a problem. I guess square root is slightly different. I also don't have a problem with square root existing here because you can actually also see quite a lot of code making use of the square root here. But yeah, and this depends on the implementation, by the way, whether you implement sine and cosine precisely or with a bit few less bits of precision. For sine and cosine specifically, it's not that hard because like they are periodic, right? You can limit your range to the 0 to half pi or even less range, and like you can do some trickery there. So it's relatively easy to do this entire range with extremely high precision. With other functions like square root and inverse square root, it's a lot harder. Yeah, but usually you don't have perfect accuracy because that's faster. Really depends on your application as well. So
don't get me wrong, but it's so alone. C tier. So what about signs? What about negation, sign extraction, absolute values, and so on? The 3 sign injection instructions solve these problems by literally injecting a sign from one operand.
Oh yeah, definitely. There's the Kaze Emmanuel video. Handy, if I think your URL would be allowed to link it in the chat if you want to link it. Otherwise, I'm going to look for it in a moment. There's a good video about sine cosine implementation and how on some really fucked up like the N64, which is a really fucked up MIPS machine, which is the precursor architecture to RISC-V in a sense. It actually is faster to do a lookup table than to like implement it with a bunch of instructions
into another operand. And fsync can also invert the sign, giving us negation. And fsync will XOR the 2 signs together, giving us absolute value. And if we inject...
this, like, when you first read this, it also looks extremely weird. That's what I love about the sign injection instructions so much.
The sign of a number into itself, we get a move. As simple as that. These are absolutely genius.
Yeah, so these are the main 3 ones that you get. You get a move, you get absolute value, and you get negation. Because, of course, there's no, like, for integer registers, a move is simply an add immediate with an immediate of 0. So you just take a register, add immediate 0, and then move that into another register, which just moves one register to another. But on... thank you, Handy, by the way, for linking the video. Kaze actually has 2 videos on it. But yeah, on floating point, for floating point, you don't have immediates. So this... by the way, there's an extension that adds a few predefined immediate loads, but that's not in the base extension. So yeah, we don't have it here. So yeah, you can do stuff like this. There's also like the signum function itself, which tells you the sign. You can implement with this. You can implement the copy sign, of course, the copy sign function with this, which is in IEEE 754. And a few others, I think. So yeah, probably there's some optimizations possible in the compiler sometimes, I guess. Yeah, but in general, there's a few really useful things you can do with these instructions.
instructions for many different common and uncommon floating point operations. S tier.
Oh, actually, yeah, the handy just said the most useful numbers are 1 and 0 is just a load of R0. Unfortunately, no. The floating point register 0 is not... Wait, am I stupid now? Okay, 1 second. Maybe you're correct, maybe you're also not correct. I don't remember. The vector register 0 is definitely not constant 0 because it's the only mask register. At least right now. 1 second. No, F0 is not special. F0 is not constant 0. So I did have that in mind correctly. So you can't actually do this. However, as we'll see in a moment, it's very easy to transfer floating point to transfer integers to floating point. So you can just transfer the 0 register into a floating point register to always load the constant, the float constant 0, and then do a sign inject or something to get the value 1. So this is as not trivial, not like you have a register for it, but it's still not hard to do.
Next, some boring instructions, just floating point equality operators. They're not branches, but only write the result of their comparison into the destination integer register, so we can use a branch equals to branch on them easily. Overall, not very special, but useful.
Yeah, this is also nice that they didn't add extra branches here, because that just always makes branch predictors unhappy if they have to now look out for even more instructions suddenly. So it's very useful if you can just do the floating point equals and then a branch if equals 0 or branch if not equals 0 or whatever, because they write the result in an integer register, right? So you can just do normal branch based on that. And of course you can fuse those instructions as well, but it's still useful to not complicate simple branch prediction.
B tier. If you're aware of the...
I specifically used a very, very evil DNB drop here, because now we're getting to like the really bad parts of IEEE 754.
The Horus, that is IEEE 754 floating
As I say
point,
here, Horus.
you're probably aware of the many kinds of numbers that it contains. Nans, infinities, normal and subnormal numbers, positive and negative 0. Floating point classify instruction allows us to distinguish the 10 defined classes of floating point values. This is a very normal thing and probably...
There's also, by the way, if you care about subnormals, I guess you can also easily find subnormals with F class here. So if you want to do anything there, I think you can probably do something really cool with like F class and then conditional move. Like if you have class 2, then you want to move like a 0 into certain register and then transfer that over to float register to like round down, basically do your own subnormal rounding. And yeah, floating point classify is one of those IEEE 754 required functions, which is not normally used. There's a specific C function for it as well, but yeah, it's generally not super important. I think it's most important, I guess, for detecting nans. So I think that's the most important use case for detecting some kinds of nan. Yeah. The handy heavily misspelled that FP classify.
Required for the standard, so no bonus points. C tier for IEEE 754 fuckery. If you read the instruction listing, this one...
I mean, I guess nan is x not equals x, but 1 second, I wanna quickly see if they actually do that properly. Signaling comparisons. I guess you're right, because yeah, the floating point equality operator will uphold the nan behavior that nans are not equal to themselves. So I guess that's true. You can do an F equal and detect nan that way. Oh yeah, JavaScript engines also use nan packing. And RISC-V also uses nan packing. This is something I don't talk about in the video, but it's right here in the standard. Do you even see that? You don't see that. Nan boxing. If your register has 64-bit integers, technically in your register, you store the 32-bit floating point stuff in nan boxed in a 64-bit float, in a 64-bit nan, which allows you to. That's how they reuse the instruction, right? Because like the lower 32 bits are part of the nan payload, so it's very easy if you have 32-bit float instructions. They always just look at the lowest 32 bits, and the 64-bit ones have like see the whole nan basically. But if you do recoded, they have some stuff here about like recoded implementations, right? Like recoded means that you store the floats internally in a different, more optimal format for your float hardware. So you might actually store it very differently. Like you are only required to use the IEEE 754 representation when you're transferring out of the float registers into somewhere where the exact representation is visible. And everywhere else, you can do whatever the fuck you want as long as you keep the rounding correct. So that's something that happens there. You can like recode it and have like different registers for 32 and 64-bit in theory, but you can also not do it and nan pack it here. Yeah. What an sprintf test expected that negative nan is a thing. Yeah, some instructions only return the canonical nan. This is pretty normal. Yeah, I mean, the point is if you have nan boxed values, 32-bit nan boxed values of 32-bit floats, and you're doing 64-bit calculations on them, then they get destroyed immediately because it doesn't really make sense. So, yeah, I mean, they immediately say that it will be immediately. Wait. Does it? No. I don't think they have to destroy the nan payload. Like, but yeah, some instructions only produce a canonical nan, so they will destroy the nan, the payload immediately. So when you have some 32-bit floats laying around, you do 64-bit operations on them, they're immediately destroyed. But I mean, after all, you're not supposed to do that in the first place. If you're trying to work with both formats, you have to convert properly. So that's fine, I guess. So yeah, I don't. Oh, an sprintf test expected that negative analysis thing. Yeah, so I mean, this is also things between like what does x86 do and what is actually required by the standard. And like the standard allows, I always say like the IEEE standard, it requires so many things, but it also allows a lot of things. It doesn't, it allows you to have exceptions or no exceptions. It allows you to produce the canonical nan or non-canonical nan. It usually only has requirements around the quiet nan or non-quiet nan, which I guess in RISC-V non-quiet nans don't exist really because they can never cause exceptions. That's like the point of non-quiet nans. So yeah. Also, yeah, there's a lot of Serenity people in the chat right now, in case you're wondering. Like Sönke and Handy, for example, are from Serenity, and a few other people that were at least online earlier. So yeah, lot of Serenity folks. Anyways, let's continue. It's already past midnight where I live, so, and we only have about 3 minutes left.
It takes up the most space, but really it's only one kind of instruction, the floating point conversions. You can convert from an integer to a float, from a float to an integer, and from single to double precision and back. Nothing special about that, basic necessary instructions that cover all cases, including unsigned integers.
Yeah, wait, no, it went away. Anyways, the point is here, always the left side is the destination and the right side is the source. So in this case, float convert from word to single. So from 32-bit integer word to single precision floating point, or 32-bit. Same thing here with long. I guess that's also weird. They don't use, or the reason they don't use D here is because it would overlap with these. So they use long here in like the C sense, which on RISC-V, a long int is in fact a 64-bit integer. So yeah. And of course you have here double to single and single to double precision. And of course you can, for these four here, you can replace the S by a D, and then you get the same thing for 64-bit floats. So like all of these take up a lot of space in the listing there, but it's basically all the same stuff. Of course, with the like integer to float, or like actually with like most of them, the only ones that don't apply is like with the widening instructions. All of the narrowing ones, like all of the first 5 here, they all also observe the rounding mode, of course, which is always the same field for all the float instructions. So that's also quite nice.
Basic necessary instructions that cover all cases, including unsigned integers. B tier.
What the fuck? Okay, wait,
Fine.
Oh, okay, something. Maybe my ad blocker just messed up. I don't know.
Finally, something that's actually a bit special. Float integer move. You might be saying, wait, that's the exact same as the float integer conversion instruction, but nope. Move means a verbatim transfer of the exact bits from the integer register to the floating point register, or the other way around. This is super convenient, especially when we consider that there's no float immediate instructions, so making a floating point immediate on the fly would otherwise be quite complicated and involve a memory load.
Yeah, so you can see in the name here, that like they use a different naming here. So this is from floating point to integer move. So the floating point word to the X, which X stands for integer or general purpose register. In RISC-V, you have like X0 through X39, X31, right? So yeah, like this is again a different naming for like the float part here. Here the float part is named W or D for a 64-bit float. But in this case, D doesn't mean double precision float. It means double word. Like it's really weird. But they use the X here to mean the integer register, and you don't need to specify the precision here because it's always the same precision. And like it kind of implies that these are not floats anymore. They're just bit patterns that are moved between registers, right? There's no conversion going on here. So, and like, yeah.
However, with the move instructions, we can construct the constant in the integer register and then transfer it over. If the
yeah, this is also one of the points. Like for example, here I just came up with some common constant like 2.5, which is in single precision floating point, that's 402 and then a bunch of zeros. So you can just Louis that without needing to fill in the lower three nibbles and just F move it. And then if you need the double precision one, that's also very easy. You can just convert it. You don't need to like construct a 64-bit immediate, which is quite a lot more complicated to do.
Constant is simple enough with a mantissa that's mostly zeros in the least significant places. It might be enough to use one Louis in an fmove.x.s to construct a single precision float in 2.
And I say it the wrong way around. It's not fmove.x.s, it's fmove.s.x, but it's actually fmove.w.x, so this is also not correct, which proves to you how like kind of confusing all of this naming scheme is. I mean, it overall it makes sense, but it's just also a thing with assembly programming, I guess.
2 instructions. Funnily enough, even the super complex x86 instruction set doesn't contain this kind of move.
And this is incorrect. Handy found just before the stream, Handy messaged me and sent me this, which is which are move D or move Q, which are x86 instructions. And as you can probably read somewhere here, it can do moves from register or 64-bit memory to XMM. And this is already an SSE. And yeah, it's also in MMX. And of course, it's also in AVX down here. So you can move, to the XMM register. So this is actually the equivalent. Like you can move from integer to floating point register. And yeah, I love this. vmove D, vmove D, vmove Q. I'm not sure if this like moves to low double word of a low double word of an XMM register. So it doesn't actually like splat it to the entire vector register. It actually just moves it to the lower part of the register, because after all, you can use the XMM registers, the technically vector registers from SSE and on, to do just normal floating point operations, which is kind of that's kind of like the weird things about x86, right? You have you have this extension that both is like for vector, but also for like the basic scalar float stuff, which I find very weird. Anyways, so my thing here with like x86 doesn't have this. That's incorrect. It does have it. I just couldn't find it. Like
x87.
Yeah, I tried to find it. It is not in x87. In x87 you can't do that. That's correct. But also x87 is an extremely weird and fucked instruction set that nobody actually uses anymore, or I don't think anybody uses anymore. Hendy can probably correct me on this. What people actually use a floating point nowadays, scalar floating point, is SSE or AVX or whatever. I mean, I think usually SSE, because it's generally available on basically every processor produced after like 2003. So yeah.
And as far as I can tell, not in SSE or AVX either. They always have to go through memory for this kind of operation. Anyways, that's a straight A tier for fmove.
And no, x87 is not just for 80-bit floats. x87 just has an extra extended precision floating point format with 80 bits. Yeah.
And here we are, all instructions from RISC-V.
You could just see there my hand going off of the green screen. There's a few situations in the video where that is the case, but this is probably the most noticeable one.
A tier for fmove. And here we are, all
cut off over here.
All instructions from RISC-V in one large tier list. A lot of
I turned to the side without knowing where it would actually appear, so I actually had to animate myself moving around. But this was actually the cool thing about the green screen. I could just animate myself moving around to get out of the way of the motion graphics, which was really, really convenient for this video. I really liked how the entire process with the green screen and the motion graphics turned out. I kind of tried to go for an Ace Roller vibe here. Ended up with, of course, something quite different still, with like my usual motion graphics style, like a mix of my motion graphics style and the Ace Roller voiceover style. Not holding a microphone either. Not making that many jokes, just a few. Like, still somewhat of a departure from what I did before, like a step up in production quality, but I really liked how all of this turned out in the end.
High tiers, and even that's relative. Most instructions here are far better than what's provided in other popular architectures. If you made it until the end, I taught you almost everything important about the most common instructions. And
yeah, there's a bunch of stuff left out if you actually want to.
And you will be able to understand some RISC-V assembly code.
Yeah, so also Ace Roller is a legend. Yeah, Ace Roller is great. If you want to learn about anything related to graphics programming, Ace Roller is your guy. It's a YouTuber. Yeah, definitely go watch him. Anyways, you will be able to understand some RISC-V assembly code. Yeah, this is a very, very strong statement, I would say. Like Domi wrote in my notes, lol as if, and linked a meme, linked like the meme where you time travel and go back in time and kill old self to learn C++ in 21 days, something like that, if you know that meme. Anyways, the point being, you don't really learn assembly code from this video. I show some basic assembly code stuff. I show a few pseudo instructions. I don't show most of the actual important ones. And that's also something people pointed out. Like, I don't actually show a lot of pseudo instructions, like the load immediate and load address stuff, and also the call and tail and ret pseudo instructions I didn't even show properly. So it's yeah, very limited. And of course, writing assembly code involves knowing at least some of the details of the encodings and that sort of shit. So yeah, even less so. But I hope you'll have like a rough idea. At least you'll know some basic instructions, at least like add and sub, I hope. Like, I also don't know all of the details constantly in my head, right? But I still have a pretty easy time just reading a RISC-V assembly code compared to everything else. So whenever I want to look at some assembly code, see how some high-level code compiles into assembly, I usually output the RISC-V code and look at the RISC-V code. It's just what I do. Yeah. And yes, of course, like, I mean, assembly programming in general is just a thing that is really hard and compared to a lot of other languages. And also it's not usually necessary. Even in Serenity, like, we usually only have to write like very small snippets with very specialized instructions. It's very easy to come up with those over the span of a few hours, whatever.
Well, okay, I guess we didn't discuss pseudo instructions all that much, which occasionally look weird but make...
yeah, so the question was, is RISC-V a good start for learning assembly? I would definitely say so, yes. I mean, any RISC instruction set is really good for learning. The problem with ARM is that there is some weirdness, and you also have to learn about flags registers. And RISC-V has very few weird things in the core ISA instruction set. It is really trimmed down. Like, you need to learn only the 40 basic instructions. In the past, people used like MIPS to teach at universities about microcontrollers. Now they use RISC-V for this exact reason. It is good for teaching. So definitely go learn that. If you're learning about x86, you immediately have to learn about a ton of weird shit that is in x86 that doesn't make a lot of sense, but just is the way it is, right? ARM post increment flags, yay. I don't even know what those are, but it sounds cursed. Anyways, yes, I would definitely recommend it. Like, in general, if you want to know more about RISC-V, we can like RISC-V.org, RISC-V International. You can become a member for free if you want to. I'm a member for free. They have all the specs are immediately available here, so you can. Yeah, I think I also linked this page. You can look at the unprivileged ISA spec here. This is the current one, 2025 one. Can read that if you want to. There's also a lot more simpler introductions into it. So yeah, there's and the profiles, I guess. Yeah, there's a lot of stuff here, but yeah, it's all completely free. I think they're under some Creative Commons license, if I remember correctly. So yeah, and they offer a lot of stuff. They hold events and conferences and shit, and you can get involved at all possible levels. Maybe I'll do that someday when I have more of a motivation. Yeah, but definitely, yeah, if you found any of this interesting, definitely go seek out more RISC-V stuff. It's very easy to find because it's so open. And if you want to work with RISC-V hardware, the best recommendation generally is get one of the ESP32C models, like ESP32C3, C5, C6 are the ones I think are available, or the P4, which is very new. These are all RISC-V based, or a CH32 microprocessor, which are also RISC-V based. So this is a very easy way. For a few euros, you can get your hands on a small RISC-V microcontroller. Write your own assembly code if you want to, or look at the stuff there. I guess you can also get Vision 5.2 or the better ones that are coming out now. like some single board computers are coming down in price now. Most of the like actual desktop stuff that can run Linux still fairly expensive. Like the dev board I have is was 300 euros, now it's 200 euros. So it's still kind of expensive compared to like getting into ARM with single board computer stuff, right? You can just get a Raspberry Pi 3 or 4 for like 20, 30 euros. But still, it's if you want to look at microcontrollers, that's very, very affordable. So yeah, let's
make your life a lot easier when programming. I hope you enjoyed this list and that you're now as excited as I am for RISC-V with its power and flexibility. Until next time.
Yeah, the power and flexibility, that's really the point, right? You can make you can allow very large, very complicated implementations to do a lot of optimizations, making it really fast. You also allow very simple implementations to work by simplifying the ISA. You have the extensions, so you can have very, very small things, very, very small instruction sets. For microcontrollers, you can have very large instruction sets for desktops and servers and supercomputers and specialized stuff. You can write your own extensions if you need something specific. If you have some kind of embedded core that does something very specific, it's very easy to use RISC-V as a baseline for some more specialized architecture. Like many architectures have some specialized functionality, but they also need to do basic microprocessor stuff. So you can use RISC-V as the basic microprocessor stuff basis, and then add things on top of it. And that's really, and apart from, of course, it being completely open source and like free from patents and so on and so forth, and free from royalties, any monetary payments, nothing like that exists. This is like, these are the main things that are so great about RISC-V. And I like, my personal hope is really that we see RISC-V being successful, not just in the microcontroller space where it's already really successful, but also in the desktop space. But let's see how that pans out. I am very hopeful. A lot of people are like, oh, but it's going to splinter because of all of the extensions. That's some of the arguments I saw on the internet recently from friends of mine. Do database management systems work faster on RISC-V? I don't think so. Like, the general point is not that RISC-V is faster than other architectures. Like, this heavily depends on your microarchitecture. It doesn't really matter if you're RISC or CISC. Generally speaking, the point is just there's one ISA that is standard and open, and a lot of vendors can compete on the same ISA base level. So if they want to sell more stuff to people that want high performance, they have to make more high performance. This is what we saw with like Intel's market dominance. Intel just got lazy, and their power usage skyrocketed, and their processors went to shit, and then AMD woke them up with the Zen architecture, right? That's the exact situation we're trying to prevent. Open hardware, yes, there is a bunch of different open RISC-V core implementations, and none of them are terrifically fast, but there are some that are decently fast and decently complex, like Berkeley out of order machines, the CVA6, which I worked on for my thesis. There's a few ones. The RISC-V International has a whole list of open source. They have a RISC-V ecosystem page, actually. Let me see if we can like see community. Is this industries, developers, ecosystem labs? Did they? No, where's the ecosystem page? Huh. Oh yeah. Milk V, woo. Oh wait, actually I didn't even, I'm reading this for the first time now, that they also have a Sci-Fi P550. Nice shit. Yeah. I mean, there's a few ones, but these are all these all still exist, but like, where the fuck is the... Oh, software ecosystem dashboard. Here we go. I think this is, or actually, yeah, this is the only one I can find right now. I guess this is only for software, but there was like a hardware dashboard at some point. Yeah, the landscape, thanks, I should have looked at the thing earlier. Landscape page, here we go. Yeah, exactly, this is what I was looking for. If we're looking at like everything below operating systems, basically. But I mean, you can already see like all the open source operating systems already supported. Even like kind of weird stuff, or somewhat weird stuff, like, I don't know, VxWorks, very specific stuff. More specific specific stuff like, yeah, the OpenBSD, I guess. And Haiku, woo! And yeah, hypervisor services, implementations. Here we go. Yeah, IP cores. This is the one I work. Sorry, not. This is one I kind of worked with the Pulpino platform. Serve is really cool. It's like a linear implementation. AI RISC is super nice because they actually have very little to do with AI. They're just a functionally safe one, I think. The Chips Alliance stuff, they have the here open hardware group stuff like a CVA6 and so on. That's something I worked on. Accelerator stuff, yeah. There's a lot of people working on this. Is Espressive is not in here, but like, of course, Espressive, like the ESP32s, they're custom implementations. CH32 has custom implementations. There's a lot of stuff a lot of people writing their own cores, but these are all just like the open source ones, or some of the open source ones. So yeah, there's a lot of stuff here. Oh yeah, Serenity is missing in the O section. Can we submit that, Sunke? Do you want to do that? I would like if you did that. You're more involved right now. I'm a member, but I don't really have any speaking power in the org. So yeah. And yeah, also some wiki article. Anyways, yeah, I just wanted to go quickly over the outro. Maybe actually let me reduce the volume. This is Light by Adromedic, by the way. Good track. Yeah, so Domi helped a lot with script review. Basically Domi reviewed the entire script, did a bunch of formulation stuff, but also things that weren't very clear, and a bunch of ideas for editing effects and stuff like that. And yeah, of course, you saw me there talking. I recorded the entire thing on my own without any help. I did all of the editing. I did most of the visual effects, like motion graphics and shit. And yeah, background VFX is either royalty-free stuff from me, and then also Anna and me did this exact background that you're seeing right now in Blender. Really, really cool thing. Like we have a particle generator that's generating like boids basically that fly in random directions. They have various colors. They have emissive materials. There's a slight background gradient, and there's like some post-processing pipeline that gives these star effects basically on those tiny triangle particles that are just billboarded, but they get this effect on them. And then also they fade in and out when they spawn and despawn, and just different ones at different distances, right? So you have larger ones and smaller ones. It's a kind of a basic effect, but until we got it how we wanted it to look, it actually took like 3 days, especially because the rendering was not very fast. But this is the first time I basically did anything with Blender. It was a lot of fun, so yeah. Kitsune has the umlaut symbol on it so that people pronounce it properly, because it's a Japanese word and it's not pronounced in English. So this is, yeah, Anna, my girlfriend, this is her third name, whatever you want to call it. No, it's not the same as for Ö in Filmröhrchen, because Filmröhrchen is actually a German word. Kitsune is neither a German, like it's a Japanese word for a fox spirit, but it's not it isn't written like that normally, but people who don't know how to pronounce it will avoid pronouncing it incorrectly. And Germans will pronounce it almost correctly based on the Ü, because it's pronounced almost Kitsune, or yeah, it's pronounced Kitsune with a very quiet high U. Let's not get into this. Anyways. Yeah, and also Anna helped a bunch with some editing decisions as well. As I say, it's based on the 2024 edition. And yeah, some further stuff. What I will link the director's cut on the left here. So if you go watching this now, you will see the director's cut here. But yeah, that's basically all there is to the video. If you have any final questions, please go ahead and ask them now. We've spent 4.5 hours on this video now. With it being like 40 minutes long, we've spent like about an hour per 10 minutes, I guess. So that's kind of, yeah. I don't know if Serenity supports that keyword that you're saying. You have to ask on the Discord. I'm not here to answer Serenity questions. I was mainly asking about, yeah, questions about the video and things related to that, the channel. Last Serenity disassembly PR when? This is a good question. The thing is, I have exams coming up, so there won't be much Serenity work from me for the next 2 months. But I hope I will have some more time next semester. Maybe I get motivation again. Also, if you like want to rebase the, or actually, I will probably tomorrow or on Sunday, I will rebase the small build fix for Alpine so that the Serenity builder can finally start working again, which is just small stuff. But yeah, the last Serenity disassembly PR is still missing. Need to rebase that. So yeah, I have, as you might know or as you might not know, I have written most of the disassembly code in Serenity for RISC-V. So like all of the RISC-V disassembly capabilities in Serenity are thanks to me, which is where I learned the cursedness of the C instruction set. Yeah, so also, by the way, if we want to switch back to the screen, if we're talking about like other extensions that I didn't cover, there's interesting things over here. You can't really read it, so I'll have to move it over slightly. I think you can, yeah, you can see it now. So the yeah, this is like counter stuff. I didn't cover this because it doesn't have instructions in it. That's pretty common. We have like maybe op, that's kind of boring. We talked about the icon. We talked about MA, and we didn't talk about wait on reservation set. This is stuff where, yeah, you can like basically wait for interrupt, similar. Here we have the CAS stuff, which I don't like, so I wouldn't have covered it anyways. There's the cache management operations, which are in the like unprivileged one because you need them from user space, but they feel more like system management stuff. I haven't read into them too much, but yeah, you can do stuff like flash caches, prefetch certain things, so on and so forth. Wait for interrupt is for saving power. Yes, absolutely. And yeah, you have FD. I didn't talk about Q, but that's just 128-bit floats. That works exactly the same as double precision. There is half precision, which works exactly the same, except 16-bit precision. There is some additional like float load immediate, which has all of these additional immediates that you can load. There's like minimum and maximum, which are slightly different, which, yeah, if either input is nan, they produce a nan, and the normal min and max don't produce a nan, but the other value, which is like, yeah, different. IEEE 754 2019 has two different minimum and maximum operations, which is why these exist, which is again, fuck IEEE 754. It just sucks so much. Anyways, there's also some better rounding stuff, which I don't, yeah, that's just you round to an integer but stay in a floating point register. I guess. Yeah, it's like weird shit. I don't quite know. Yeah, this is like round to integral exact. This is another extra operation. Then the modular convert to integer, which is also some extra things, whatever. And there's also some modified comparisons. And then you can also put floats in integer registers, which is its own other thing. Then again, compressed instructions, we talked about this. There's some more extra compared instructions, like we have the push pop sequences here where you can push and pop multiple registers, stuff like this, right? Like you might know this from ARM, very similar, not compatible with G, but useful for some microcontrollers. We have the B extension is the big one that I maybe should have talked about, I guess, or could have talked about. The thing is, it's just, yeah, a large list of random shit. There's like, yeah, add unsigned word. All of these are like, if you look at the encoding, they're like slight modifications of existing instructions. They're not very different. Like here, add with inverted operand or with inverted operand. You have, of course, actual bit manip instructions like bit clear, bit set, bit invert. You have carry less multiply, count leading zeros like pop count, count leading ones. Here, pop count, maximum and minimum. What else would you have? Bitwise or combine. I have no idea what exactly this is. Some packing stuff. And yeah, like there's some byte reverse or bit reverse stuff for like converting endianness and so on. Rotate instructions, as I talked about. Yeah, sign extend byte, as we said, is very easy to implement with set less than, but you can also have a separate instruction for it. You have the shift and add, which are for address generation. I talked about this. Unzip, some permutation like lookup of integers, indices in like register vector, I guess. Yeah, like the crossbar permutation stuff. Not actually sure, what does B specifically contain? There's ZBA, BB, BC, BS, and the other one. I think, yeah, just these 4 ones, and then the BKX. Yeah, this is like stuff for cryptography, right? And crossbar manipulations. Those will probably not be in the standard that much because they're not terribly useful outside of cryptography. And then, of course, we have a working draft for some pointer tagging stuff, and which is useful, yeah, for storing like, yeah, for pointer tagging in garbage collection, so on and so forth. There is like a long-standing, what is it called? A long-standing draft for this. Basically, you can like tell the hardware, okay, I have a tagged pointer here, and just ignore some bits from the pointer and just not use it for addressing, which is sounds like an extremely useful thing. I would definitely be for this extension here. Like, I don't disagree with like doing this kind of special optimization for Java and JavaScript. Like, these are extremely commonly used. Like, this is useful for a lot of garbage collection stuff. It's also useful for Go and other languages. Most of the stuff runs in browsers anyways, so might as well. SUPM is ratified, which is pointer masking. Yeah, okay, so there's a different or a similar pointer masking extension, which is ratified, but that is a supervisor extension, and we want something that we can use from user space, right? So that's slightly different. Anyways, there's a packed SIMD, like they're working on packed SIMD, basically, yeah, putting vector stuff in normal integer registers, but this is probably not going to be very widely used again. It's going to be for specific use cases, not for general purpose stuff, because general purpose is just going to have V, which is the very next thing. V is very large, but has some really cool stuff in it, like the yeah, it's super complicated. You have different sizes and different element kinds and grouping shit and tail and mask agnostic stuff and masking and there's so much stuff, just so much stuff. And you have the vset VLI, vset VL instructions here. Where did they specify that? Not sure. Like, yeah, vset VLI is like the stuff specifies, yeah, you can do very, very cool stuff with like processing array SIMD things. You probably have to look into this yourself. It's pretty cool. It's very similar to what's it called, scalable vector extensions, SVE, in ARM. So the vector register size is not fixed. It has to be at least 128 bits if you implement V, but it can be smaller or larger. So you can like this is something where like very, very large, very powerful servers can in the future easily say, okay, we're going to have larger vector registers, and the software automatically, hopefully, if they write their code properly, will automatically make use of it. That's really cool. So I'm generally, apart from the fact that masking is kind of limited, a vector extension is really good, but like it's kind of unavoidable that it's becomes very complicated. You can see they don't even describe all of the instructions in detail because there's just so many of them. There's so much stuff. Like you can see, it just goes on, it doesn't stop and doesn't stop. And yeah, cryptography, there is some scalar cryptography stuff. You can see like SHA-256 things here. There's also things for specifically for Chinese cryptography suit, yeah. But it's also, this is just a group basically for yeah, some Xiangmi stuff. But luckily the standard scalar stuff is NIST and not Xiangmi, because like you can tell really in RISC-V, like China has a lot of influence on that. And yeah. Anyways, the main thing that's going to be available a lot is the vector cryptography extensions. And yeah, they have a lot of shit here as well. Pretty much the same stuff, but just for vector registers. And what is my OpenSSL? I did talk about OpenPGP, which is absolute garbage dog shit. Anyways. I think that's basically all of it. There's a bunch of other extensions that are not in here that are ratified. There's also like the privileged stuff. So yeah, keep a lookout for that, I guess. And yeah, go watch the other videos, or go watch the original video. I'm going to copy the link again. And paste it into the chat. So yeah, that's it for me. Have a wonderful rest of your day, and I will see you hopefully soon with another video. Let's see if it's going to be about Stardew Valley, or about FLAC, or about Alia Aquarius. Maybe the new book is coming out. A bunch of different stuff that I want to do. Let's see. Until then, goodbye. Have a good one.